Is aging a disease? Is that even a relevant question?
Calling me. So calling aging a disease is a fundamental error.
The question itself is incorrect.
I agree completely. I think it's the wrong question.
I agree, but
how do we define health span?
I haven't seen anything to make me believe that you can separate health span and lifespan.
My own personal answer to that is it's a useless term.
A state of your physical being that you can do the things you like to do.
The United States has the lowest life expectancy. That's because the United States has by far the greatest rate of death in middle age.
And I mean, the reality is the research flows from where the dollars are going. This has been seen over and over and over at NIH.
Maybe it's because the public doesn't understand this. But those people answer to the public. Because I'm in the mood to see you get spicy. Can we just talk about senescence for a minute?
There's no evidence, as far as I know, that it either has an anti-aging effect or removes senescent cells.
Let's do the closest thing that a group like this could do in terms of a speed round. Hey everyone, welcome to the Drive Podcast. I'm your host, Peter Attia. Gentlemen, this is a lot of fun. I am excited to be sitting down with you guys today. Where do we want to begin? I mean, let me start by saying the following. The term longevity, someone sent me something the other day that was like list of, I don't know, whether it was how many times the word longevity was searched on Google or something like that. But it literally looks like Bitcoin. So we are clearly at peak longevity in terms of public interest, which for all of you who have kind of devoted decades, plural, to this, I just want to kind of get a reaction from you, each of you, on what that means, why you think it's happening, and maybe even extending the metaphor a little bit. Is there a bubble going on? So we'll start with you, Steve.
Yeah, well, it's a surprise to me that longevity has become so big because for a long time we sort of tried to move away from that in the aging field because we were worried that people were thinking of longevity as, well, we're going to keep frail, feeble, old people alive longer. That's what longevity meant, when really what we were trying to do is extend health. And so I'm kind of surprised, but I think it's because there are certain people of a certain age who've started to think about their own longevity. And then I think there's a whole new generation of tech entrepreneurs that really feel like this is a problem that will allow them to live healthily for several decades, at least longer than they are now. So I think it's a combination. It's a multi-generational thing. That kind of surprises me.
And you haven't seen this before, to be clear. So 30 years ago, you didn't see glimmers of this? 30 years ago, I would have said, let's not even say the word longevity. Let's say health span. But that's changed quite clearly as more and more people have been, from the outside, they're sort of peeking in at the field. I don't think the people in the field itself have changed the way they talk that much, but the people eavesdropping on the field certainly have. Rich, is that your experience?
Well, I think there are two aspects that I would want to emphasize in response both to your question and then to what Steve said. In response to the question, I think the reason that people have always been fascinated for millennia on things they could do to stay alive and healthy as long as possible. But there were actually scientific discoveries in the 90s that showed that it could be done. And then in the last 20 years, there's evidence that it can be done, at least in mice, with pills. So that naturally should lead to speculation that there could be pills you could give to people that would postpone poor health for a substantial amount of time. 20 to 30% is what we're seeing in mice, and 20 to 30% would be very important for people. So I think that is a part of it. The other part is that there are now people who are making a lot of money by selling stuff that is untested, to be polite about it, or is useless, to be less polite about it, to gullible customers. And so people who want to make a lot of money have finally found that there's an impetus that will allow them to sell stuff even if there's no evidence that it works, that they control an enormous amount of advertising dollars, both formal and informal. That's a big part of the difference. The one comment I wanted to make with regard to something Steve said has to do with the alleged balance between health span and lifespan. It's become fashionable for the last 20 or 30 years to imagine that you get one or the other, that you have to make a choice. It's a decision. And that if you give up on lifespan, that allows you to extend health span. I think that's ridiculous and controverted by all the available evidence. That is, all of the drugs, at least, that extend lifespan in mice and could potentially do so in people, do so by postponing diseases, both the diseases that will kill you, that's why they extend lifespan, and the diseases that won't kill you, but which will annoy you and make you very unhappy to be old. So,
which is true, by the way, of non-molecular tools as well. I mean, that's
absolutely
true of exercise.
Yeah,
and
absolutely. That's a good point.
Not being insulin resistant.
I agree with you. So the notion, it's time to put behind us and to make fun of the notion that I'm not interested in lifespan. Don't put me on that boat. I am interested in health span, because they are linked together and they go up and down together. Getting people disabused of that false metaphor, the seesaw metaphor, is probably an important goal for sort of the public interface between longevity scientists, aging scientists.
Now, I just want to push on one thing, though. You talked about, obviously, the discoveries of molecules. You've been personally central to that work. But there was still a lag, Rich, right? I mean, it was 15 years ago, the first ITP was published showing the overwhelmingly surprising and positive results of rapamycin.
Yes.
Those results were repeated.
Yeah.
So why a decade? Let's be generous and charitable and call it a still decade-long lag from that. And by the way, I'll throw one more thing in there. If you go back to Cynthia Kenyon's work, which may have 93. Been the thin end of the wedge into the idea that lifespan was malleable, albeit through a genetic manipulation in a less relevant model, there's still a lag. And again, do you buy Steve's argument that it's a confluence of technology, tech entrepreneurs, new problem to work on?
Let me answer your question first. Why the lag? I think there's a whole batch of reasons, and they're important and they're easy to spell out. One is that the prevailing attitude is that aging is there. There's nothing you can do about it. I'm gonna not be able to outwit aging, though I may be able to be maybe healthier in my older years. The notion that aging is not malleable, though wrong and provably wrong, is still the overwhelming opinion, even of reasonably educated scientists and certainly of the lay public. Then commercially, there are companies that make a ton of money selling stuff that doesn't work by pretending with a wink and a nod and a lawyer that it might slow the aging process down. And since they can make a lot of money, they don't actually have to spend valuable marketing dollars on doing, research and stuff to prove that it works. Some of the drugs that, at least in the hands of our mouse group, the ITP, Interventions Testing Program, some of the drugs are, the patent is owned by another company, or they're out of patent, or it's a natural product. None of that says, take me to whoever owns a big pharmaceutical firm. And also, even if you do it right and you really want to do it and you've got a very large budget, it's not an overnight kind of thing. Any one drug, a leading agent that, like rapamycin, which you mentioned, and the half a dozen others that we've shown work, at least in mice, finding something in that same family that works really well, that is safe for people, that's the member of the 20 congeners of that drug that's best and most potent and safest, that's not at all trivial. That takes a long time, and it takes a commitment of money and time and effort and intellectual resources. We're at the place where we can start to make an argument that that's a good idea, but making an argument that that's a good idea to people who actually have the resources to carry it out has not so far been enormously successful, unfortunately.
Can I push back a little on what Rich said about health span versus lifespan? There's several papers that have come out recently showing that the gap between health span and lifespan in people is actually increasing, and it's increasing the fastest in the United States, and it's increasing faster among women than men. So in humans, this is a very real gap, and it's a growing gap. And I think one of the advantages of the kind of the geroscience, the stuff that we do, is that Rich is right. We don't see this in our experimental systems. So this, to me, emphasizes the fact that we need to change the focus. I think one of the reasons that the gap exists is we're getting better and better and better at treating heart disease and cancer and all these things and keeping people alive when they wouldn't have been alive 10 years ago. But this is a really important factor, I think, about thinking of public health globally.
But it's important to see. Go ahead.
I was going to say, I think you're both right. I think you're looking at it from different angles. So, Steve, you're pointing out that you can make people live longer when they're sick. I think what Rich is saying, which I agree with, and hopefully I'm going to paraphrase you correctly, which is if we target the biology of aging, I haven't seen anything to make me believe that you can separate health span and lifespan, meaning that I haven't seen things that slow aging, increase lifespan, don't increase health span. I don't actually think that's plausible.
No, and I think that's an important point, that if we target aging, we're doing something different than with the way that medicine is operating now, which is targeting individual diseases after they occur.
Right.
This is a very important point. It came up in a recent podcast that I did with Sam Sutaria talking about healthcare costs. And in that discussion, one of the things that emerged, which I think most people are sadly familiar with this statistic today, is that among the OECD nations, the United States has the lowest life expectancy, which is ironic given that we are spending on average about 80% more, and in some cases double what most other developed nations spend on healthcare. So how do you reconcile this? Well, Sam made a very interesting point, which is that's aggregate life expectancy. But why is that the case? That's because the United States has by far the greatest rate of death in middle age, right? So when you look at maternal and infant mortality, we're horrible. When you look at gun violence and suicide and homicide, we're horrible. And most of all, when you look at overdoses, we're horrible, right? So when you kill a whole bunch of people in their 40s and 50s, you cannot have a very high life expectancy. Understood. But what Sam pointed out was once an American reaches the age of, and I forget the exact age, I think it was about 65, all of a sudden they jump to the top of the list. That was very interesting to me. In other words, if you look at the blended life expectancy, we're not doing very well. But if you look at life expectancy, just in measured as years alive, once you escape those big causes of death in middle age, we actually do quite well. And it comes down to what you're saying, which is we get very good at delaying death in chronic disease. That's what I call the medicine 2.0 machine at its absolute finest. We are going to keep you along an extra 6 months once you have cancer. We are going to get you through that third revascularization procedure. And so now the question is, does that, because my intuition is where yours is, Steve. I don't think we're getting any healthier, even if we're incrementally figuring out ways to extend life in the face of chronic disease. I don't see it being a quality of life. Now, part of this might be, how do we define health span?
Yeah. So I agree with you. And I think it's even worse though than the way you laid it out. So if you look at the statistics, if you accept that 60% of Americans have at least one chronic disease and the median age in the United States is 38 point something, and then you think about how long are people living on average, that would suggest if you say that, and again, this is what you're getting at with the definition of health span. I would not define health span as ending once you have your first chronic disease, but that's the definition most people would use. If you use that definition, most people are spending 3 decades or more in the absence of health span, right? Or in sick span. So, I mean, the situation is, even in the United States where life expectancy is relatively short compared to other nations, a big chunk of that life expectancy is not spent in good health, and it's exactly for this reason.
But there are two different issues that are being confused here in the discussion. One is the issue of whether you can help middle-aged people live longer. And everybody's agreed that we're getting better at that. We're pretty good at it. And that certainly contributes to whatever you think health span might mean. That's an issue, however, that is quite different from what a concoction that slows aging do so by extending health span. Those both have the word health span in them, but they're different and shouldn't ever be confused with one another. The other point in this question you asked was, what is health span? My own personal answer to that is it's a useless term. That is because no one can define it. It's not because no one is smart. It's because the term itself is vacuous and nebulous. If you have somebody that gets a certain chronic disease here and then another one, and then they fall down and bump their head, and by the way, they go to the hospital and with COVID, et cetera, defining when in that broad, over that 20 to 30-year period, they flick the switch, now they have gotten to the end of the health span, is impossible and of no interest. The general notion that people are interested in is whether you can do stuff to keep people healthy for a long time, either without changing their life expectancy or by changing their life, with changing their life expectancy. Those are interesting, but you don't have to assign a number.
But couldn't we get away, because I agree with you completely, Rich. I don't like the medical definition of health span, which I believe is, quote, the period of time in which an individual is free of disability and disease. I find that to be a very unhelpful definition.
Yeah.
But part of the reason it's awful is it's binary.
Yeah,
and
exactly.
That's silly. But if we made it analog instead of digital,
right?
I'm not saying that makes it easy. It's still very challenging, but now it allows us to start talking about things, right?
As a person, except it's a concept. It's a qualitative concept, right? I mean, I think we should try to make it to where we can actually come up with a way to measure whether we call it health span or not. Yep. That doesn't really matter. But I kind of agree with Rich. Like I agree with what you're saying, except I think it's a really useful term as a concept. I think it's a really useful way to communicate to a broader audience what one of the goals is, right? Which is to increase the healthy period of life.
Yeah, I kind of like the term health for that. I have a way that helps you out with your health. And you don't have to
maybe it's
pretend
function.
You can define it as a number.
But there is a period of, I think we all could agree, there's a period of life where you are in relatively good health. And then there's a period of life where you aren't. And so I think the idea that we're trying to increase that component of life is really important. So I don't think we're actually disagreeing on much other than whether we like the word. Right?
Well, I also think there's an individualization of this that we're missing. To me, health is a state of your physical being that you can do the things you like to do. And therefore, if you like to climb mountains, your health span is going to be different than if you like to play golf, for instance. And a lot of this is personal. You know, if you can't run a marathon anymore, some people will say, oh, my health is...
And we never pay attention to the mental health piece. At least the biologists don't. Right?
So I have a question for you, Steve. What is my health span?
I mean, I would only be able to ask you that.
Well, I can.
So we do this exercise, guys, because I completely agree with you, Steve. Yeah. We call it the marginal decade exercise.
Okay.
So we say to every one of our patients, and I write about this a lot in the book, right? Everyone will have a marginal decade, which I define as the last decade of your life. So obviously, by definition, everyone has a marginal decade. Most people do not realize the day they enter it, but most people have a pretty good sense when they're in it, right? Okay. So the exercise we do is we go through with the patient and we say, what are the things that are most important to you to be able to do in your marginal decade? And they generally fall into 3 buckets with a sub-bucket: physical, cognitive, emotional, social. The physical bucket we kind of divide into activities of daily living and recreational activities. So that's where, again, most people obviously intuit that, boy, I would really not be happy if I couldn't take care of myself. If I couldn't get out of bed, get dressed, shave, cook, like that would be disappointing to me. But then, of course, you have different levels of ambition within the recreational side. And I've got patients who say, when the day comes that I can't heli ski, I'm going to be devastated. And other people are like, I just want to be able to garden, right? So that is going to create a very different standard. On the cognitive side, you have people who say, I want to be able to run my hedge fund and still make money and make really important investment decisions. And other people are like, I want to be able to do crossword puzzles and read the newspaper. And that's my standard. And again, we can go down. So this is why it's I agree with you. You can't define it, but it doesn't mean we shouldn't try to personalize it. Okay, but I want to come back to you, Matt, with the original question.
Was the original?
No, the original question. Why are we at a point where I don't, again,
why has longevity gone mainstream?
Yeah, for lack of a better way to describe it.
So, I mean, I think both of the points that Steve and Rich raised are part of the equation. I mean, I think it's a convergence of all of these factors and maybe a few others. I do think the science has matured to the point where more people are believing that we can actually modulate the biology of aging. I think the concept of biological aging has become popularized through a variety of mechanisms, including, some influencers, individuals who I personally think often err on the side of being a little bit less scientific than they should be, but I think they've helped popularize the concept. So I think it's been a combination of these factors. And why it has taken so long, I just think that's the pace that, science moves and the rate at which these concepts can sort of permeate the public sphere. So it's frustrating in a sense that it's moved so slowly, but I do feel, and I also wonder, because you sort of said, are we at a longevity bubble? I don't know. I think maybe we're still kind of in the early days of this sort of hockey stick moment, right? Where you're getting this exponential increase in attention. My hope is, as we go forward, it will become more scientific and less snake oily. And it's a spectrum, right? There's this huge gray area in the field right now of what's real and what's not real. And I think none of us at this table actually can really define exactly where in that gray area that line is, or is there a line? So
to that point, Matt, what is the collective wisdom of the group on the funding appetite for that? Because I agree with you completely. Like, if we could channel this exuberance away from kind of the highly commercial, speculative grifting towards the budget increasing, legitimate investigative, that would be awesome. What is the appetite right now of NIA with respect to this?
I think it's hard to say it. And NIH is a moving target. And as we all know, that there's going to be a lot of change coming in the near future. So cautiously optimistic, I would say. If you look historically, it's been really pretty terrible, right? The percent of NIH budget that goes to biology of aging, I think, is still probably around half of 1%, even though biology of aging is the
Sorry,
greatest.
Just to put numbers in perspective, do you know these, NIA gets what percent of NIH?
Not NIA.
No,
so
I understand.
Within NIA,
yes,
there's a sub-fraction that goes to biology of aging, right?
Yes.
Yeah.
But I'm saying there are 17 groups of NIH, NIA being one of them, gets what fraction of NIH budget, roughly?
I think it's roughly 3%.
3% of NIH budget is NIA. Within NIA, how much goes to this type of research?
It was about $350 million a few years ago. It might be a little higher than that, but I don't think it's ticked up any more proportional to the increase in NIH budget since then. So that it reaches about half of 1%.
Wow. What's your level of optimism, Rich? You're obviously very close to this.
That NIH will wake up and start to pay attention to aging research the way they should. It's near zero. It's been near zero for 30 years now.
Even with this,
the reason is,
that's outside attention.
Well, it's gone up. They funded the ITP, the Interventions Testing Program, 20 years ago, and they liked it, and they doubled our budget about 15 years ago. So that's something. And I'm very, very grateful to them for that. But there's still an enormous untapped potential for making progress in the basic biology of aging. And the reason is, again, a matter of defending turf. If you are a cardiologist researcher or an oncologist researcher or an AIDS researcher or an Alzheimer's researcher, anytime somebody says, the smart play is to reduce your budget by 10% or your institute's budget by 10%, we're going to go there faster if we spend money on aging and its relationship to the disease you care about. You get the porcupine defense. You don't take any of my money because Alzheimer's is important. Little kids with leukemia are important. Breast cancer is important. You go away. And that is the predominant feeling. Most of the people making those decisions were not trained in aging research. They view it as something interesting. I read something about that in Time magazine the other day. But they don't understand that to actually conquer or slow down or affect or protect against the disease they care about, the smart play is to do aging research. And so they view your suggestion, which I, of course, agree with 100%, as an imposition, an invasion to be repelled at any cost. No one in a position of power has had whatever it takes to reverse that. And if he or she tried to do that, Congress would, even a good Congress, would smack them down. The Alzheimer's group has 100 lobbyists. The cancer group has 100 lobbyists. The AIDS group has 100 lobbyists. The aging group has 2 lobbyists, one who's a lawyer and one who takes the calls, and it's not enough to do it.
Can I just add something real quick to that too? Because I agree completely. And I think as well, the reputation of the field has hindered that transition as well, right?
Yes,
so
absolutely.
Historically, the field was viewed as not very mechanistic, kind of phenomenological, became much more mechanistic starting around the time of Cynthia Kenyon's work and since then, but has continued to have a reputation problem as not being as rigorous as other areas of research. So I think it is absolutely a turf war. And there's this overcoming the reputational problem, which makes it harder for serious people in funding and policy circles to give it the attention it deserves, in my opinion.
So I've got a different take on this. I actually think that this is a very good time for aging research funding. And that's not because of what's going on at the NIA, but it's what's going on in the private sector. There's more and more money. There's even interest now in big pharma. And that's, that was very spotty in the past. So I think if we focused entirely on the National Institute on Aging, we would get a false impression of what the funding climate is in the field now. And I think we need to take advantage of that. We got to make sure that it doesn't get captured by the people who are doing the flashy but bad science. That concerns me.
So you're saying, look, Calico, Altos, other private companies, especially within biotech and pharma that are looking at geroprotective molecules, building on the work of the ITP. Yeah, I think it's safe to say the amount of money that's being spent privately probably outdoes public spending. I mean, in a given year, 2 to 1 easily, right?
It could, although how much of that is actually going to biology of aging, I think is still an open question. You mentioned Calico and Altos, right?
We don't know exactly what's going on.
I mean, I actually agree with Steve. I don't think what Rich and I were communicating is opposed to what Steve was communicating. There are a lot of opportunities right now. And again, this is sort of what I was alluding to is, are we at the beginning of this hockey stick moment? And I think Steve's right. There are real opportunities for more resources to be focused on the scientific side and hopefully less focused on the non-scientific aspects of what are going on. And you asked the question of, can we shift resources from the more consumer-facing, maybe not as rigorous stuff and into the more rigorous stuff? Maybe you need that sort of. I mean, again, I'm not a fan of that stuff at all, but maybe you need that stuff to kind of move the needle and get people's attention. And at least people are talking about longevity now.
Naive question, and I'm embarrassed I don't know the answer because I spent more than 2 years working there. What's the mission statement of the NIH?
It's to preserve and enhance human health. I mean, it's basically the same thing that we do, that we're supposed to be doing.
Yeah, and I didn't actually get to give you my spiel here, but what I started to say about the NIA budget is if you look at the major causes of death and disability, and it's, again, we talked about how it's hard to define healthspan. So if we just look at causes of death, right? If you look at the top 10 causes of death in the United States, 9 of them have biological aging as their greatest risk factor. And it's not even close. Yet, half of 1% of the research budget that's supposed to be focused on improving human health goes to study that risk factor. And I mean, I think it is extremely frustrating to all of us sitting at this table that hasn't changed, but there's reason to be optimistic that maybe it will change in the near future.
Let's state that again because it is so profound. I want to make sure not a single person missed that statement. The top 10 causes of death in the United States are well enumerated and incredibly predictable, and they increase by category, by decade, 3 to 8% monotonically with no exception. Point being, 90% of, and more than 90% on an adjusted basis of what causes death goes up with age. And yet, a few basis points of federal R&D goes to addressing that.
Let me give you an example of what the sort of point that Matthew and you have been making. About once every 5 years, I give an invited talk at the University of Michigan Cancer Center, and I point out that we have drugs now, anti-aging drugs, in mice, and they extend mouse lifespan, and they do it mostly by postponing cancer, because most of our mice die of cancer. And if you look at age-adjusted cancer incidence rates, our drugs reduce these by a factor of 10. Wouldn't they like to know why? As cancer scientists, we now have a batch of drugs that postpone cancer. Wouldn't they like to study them? Invariably, I get one call back from somebody who says, that's interesting, maybe we should talk about that. And then it dies. And then 5 years later, I'm asked to give the same talk or a related talk. So they know how to do cancer research. They are cancer scientists. That's how they know how to do cancer research. And you certainly don't do it by diverting your lab's attention to aging. That's insane, but that insanity is how medical research is organized. And breaking that addiction to the kinds of models you grew up on because they're a better idea is not a trivial, not an easy thing. It may not even be a possible thing to do. That's a major hassle.
Well, I think this is because we think about health all wrong. We think, let's wait till you get cancer and see what we can do about it. That's what cancer biologists do. You have cancer, okay, how can we better treat that? Or could we have diagnosed it earlier? What Rich is saying and what we can know how to do in lots of model organs, it prevents you from getting cancer, delay it for a considerable amount of time. That's a little bit harder to study if you're a cancer biologist, because you want to see the cancer before you can study it. I think that's why we need aging biologists rather than people focused on certain disease to come and try to use what we do to, if we prevented the cancers, they'd be out of a job.
I guarantee these people or mice will get cancer. They'll just have 10 extra years of life if they're a person, or 10 extra months of life if they'll get cancer. They'll need specialists. It'll be all right.
Yeah, I think that's important. I mean, I think the reactive disease care component is still going to be there, right? Even if we're insanely successful at slowing aging, people are still going to get sick. But I think Steve's point is really important. Like, Peter, you've been a leader, right, in helping people recognize the need to shift the medical approach from reactive to proactive. I think what a lot of people don't realize is that mentality goes all the way back to pharmaceutical research, biomedical research, basic science. That is ingrained all the way through. And I think one of the challenges with getting funding for aging research is that mentality on the basic science world and how deeply ingrained it is.
It's very interesting because you don't know which is the tail and which is the dog. Like, I've always assumed that the one leading the charge is the clinical side of things, right? In other words, the engine, the machine of medicine 2.0 is built around the delivery of care. The delivery of care, as you said, Steve, is built around, I'm going to wait, I'm going to sit here and hang, we're going to wait. When you get the disease, we're ready. You had the heart attack? Fantastic. You've got chest pain, ST elevations? We got a stent for you. Now you have cancer? We're all in. And then the research flows from that mindset. Of course, I don't know, not that it really matters, but it might be that it's flipped, right? It might be that the clinical engine behaves in that way because that's how the base of the pyramid has been built. Again, not that it necessarily matters, but if you could be health czar and fix one of them, you might actually start with the research side of things.
I would. And I mean, the reality is the research flows from where the dollars are going. This has been seen over and over and over at NIH. You shift resource allocation to a certain area and the scientists will follow, and they will submit grants to get grants in the place where the funding line is the highest. So if somebody came along and said, we're going to go from 0.5% to 50% of NIH budget is going to go to biology of aging, you'd have no shortage of people. I mean, it'd be kind of messy at first, but you'd have no shortage of people applying for grants and becoming experts in the biology of aging.
And the system would work. You'd get the best and the brightest that would go into that and do that. So this then begs another question that is a tired question, but I can't help but ask it at this point. Is aging a disease? Is that even a relevant question?
Calling me. I
yes, Mr. Miller.
Calling me. It's important to use words optimally and to distinguish causes from effects. One of the bad things about aging is it's a risk factor for many diseases. Some things, other risk factors for diseases. Aging is a risk factor for disease. And so saying that aging is a disease confuses that discussion. It makes it impossible to see that relationship. So calling aging a disease is a fundamental error.
The question itself is incorrect.
I agree completely. I think it's the wrong question.
I agree, but I think we have that idea for marketing purposes, not for scientific purposes. And the idea is, well, the money goes to diseases. Let's call aging a disease. Because I think what we're trying to do is we're trying to treat aging as if it were a disease, even though I would agree with both of you. I don't think it's a disease. I think that destroys the word disease if we include aging in it. But I think there was a reason that suddenly this came because you thought, oh, maybe this will get Congress to pay attention.
You're right. It's a marketing ploy. And if you think you can convince people of the importance of aging research only by crossing your fingers and saying, oh, well, it's kind of a disease, isn't it? And you think you can fool them? Yes, that's what marketing is, and it's probably good for that. I just don't like lying to people.
It also creates a negative feeling about the field in some people as well. So I think that should be considered. The other point that people often raise, though, is we have to call aging a disease in order for FDA to approve a drug for aging, which I think is a fundamental misunderstanding of how FDA operates, but that is the other argument you will often hear among proponents of the idea that aging is a disease.
Very interesting. Okay, so now let's go one step deeper on that. How do you think about biologic versus chronologic age in concept and in practice?
Yeah, so on the ride over here, Rich and I were talking about that. I don't believe there is such a thing as biological age. I think there is potentially an age of your heart, an age of your liver, an age of your lungs, an age of your brain. But I don't see why we wouldn't simply call it health. In other words, I got one of these epigenetic age clocks done on me a while ago, but I didn't know what to make out of it. I thought, is this just flattery? I want to do this, or did it really tell me something?
You must have got a good result if you thought it was flattery.
Huh?
You must have got a good result if you thought it was flattery.
Result.
He's 13.
But
13 years old.
That may be the point of the whole thing, right? So I'm dubious about some number that is different than, I know I'm in good health. For my age, I'm in very good health. So I knew that already. Now I have a number for it. I don't put much credence in that number.
Let me agree with Steve, but just put it in slightly different terminology. It's a matter of taking a very rich, complex data set and trying to collapse it to a number. So if someone wants to know how healthy I am, he or she would need information. How good is my eyesight? How good is my hearing? How good is various kinds of cognitive activities, my aerobic endurance, my ability my joints, all of that is pertinent to how my health is and also about projected future health. Then there's no need, once you've got that information, which is very rich, to say, there's a number, a single number, a real number, on a point on the number line that condenses that in any useful way. The notion 40, 50 years ago that biological age was not the same as chronological age, for a little while was useful. It emphasized that there might well be 60-year-old people who were unusually like youthful people and 60-year-old people who were unusually like 70-year-old people. Would my drug or my genetic mutant or whatever help to discriminate those people or change them in some way? I can slow your biological aging process. That's a discussion that was maybe of interest 40 years ago, and it's now time to drop the notion, let alone the silly notion that you can count that biological age, that number which too many people still think is of value. You can figure out what it is by measuring something, transcriptions or epigenetic markers or something. I can do it and give you personally your personal biological age. That's a waste of everyone's time, and it also distracts attention from things that actually are important and need to be thought about.
I got to talk because I think I disagree fundamentally, and I'm surprised, but this will be an interesting conversation. So I agree that the idea of a kit that you can buy to measure biological age, first of all, the stuff that's out there doesn't work, and we can and should talk about that.
Yeah.
But also, I sort of agree with the idea that reducing it to one number, while conceptually I think it's possible, I think in reality is going to be really, really difficult to do. But do I believe that there is a biological aging process that is different from chronological aging? Absolutely.
Oh, yes, absolutely.
Okay, well, it sounded like you guys were both saying no. You didn't think it was a real thing.
I agree with that completely. You can agree with that and not like the idea of a number that constitutes your biological age.
Okay.
Yeah.
So there's two things that kind of make me feel pretty confident in this idea. One is, and this is the example I use a lot among the general public, is just look at dogs compared to people, right? Everybody's familiar with the idea that 1 human year is about 7 dog years. What does that mean? It means that dogs age about 7 times faster than people do. But of course, chronological time is the same between dogs and people. It's the biological aging process. And so you can look across the animal kingdom and see this. And dogs get almost all of the same diseases and functional declines that we do at the tissue and organ level, but also at the whole body level. And we also know now there are single genes that significantly modulate what I would call the rate of aging. Now, maybe we have a different meaning to what we mean that.
No, I agree entirely, yeah.
So the fact that that's possible,
Right.
DAF2, we talked about DAF2 a couple of times, TOR, we can turn these things up, turn them down, and animals across the evolutionary spectrum seem to age at different rates by modulating single genes. So I don't know of any other explanation other than that there is this process, which we call biological aging, that can be changed, and the rate can be sped up or slowed down. Can it be reversed? That's an interesting question. Maybe we'll get to that. But I think the process is real. I think it's just really, really complicated, and we probably only understand 5% of it at this point.
For me, the challenge is I kind of land where Rich was, which is if a patient says to me, hey, why aren't you doing this biologic age clock on me?
Yeah.
My response is, well, I know your VO2 max, I know your zone 2, I know your muscle mass, I know your visceral fat, I know we did a very complicated movement assessment on you, I understand your balance, I understand like your lipids, your insulin, like I know these 57 things about you, and I can tell you individually on each of them how you're doing. That number doesn't tell me a single new piece of information.
But what if you were to come up with, and then you probably do this in your head, right? You come up with some sort of composite, right? You probably don't sit down and weight each of those things and come to one number, but you come up with some sort of composite picture of health based on all of those things. That's a different biological aging clock. I think sometimes we conflate, and in part this is because of the way that irresponsible people in the field and marketers have done this. We conflate the epigenetic tests with biological aging clocks. There are all sorts of flavors of biological aging clocks, including things like frailty indices or metrics of a whole bunch of functional markers. So I think those probably are pretty good readouts of biological age. Again, can you combine them all to get to one number that's meaningful for every person? That's much harder to do.
Yeah, tell us about your experience, because this was, I thought, you did what I wanted to do, but I've been too lazy to do.
Yeah. In fact, we exchanged emails at one point about doing this, and each coming up with different names. So So what I did was I tested 4 different direct-to-consumer biological age kits. They were all epigenetic biological age tests, 4 different companies, and I did duplicates of each kit, and it was from the same samples collected on the same day, right? So really tried to put my scientist hat on. I only had 2 replicates. I didn't have 3 replicates, but it's about the best I could afford at that point. So, and it was kind of expensive. So anyways, sent those in, got the results back, and they were, to me, very informative, fundamentally sort of changed my views on these epigenetic age tests. So they ranged from 42 to 63. I was like 53.75 years at the time I did the test. And the standard deviation, I can't remember, it was either 7 or 9. So mean of my chronological age, standard deviation of 7 or 9, which, I look at that data. I'm not a statistician, but I know enough statistics to say that's completely useless. They converged on my chronological age, but with a huge variation. And
even
so that varied between the tests. So I think 3 of the 4 were reasonably close to each other. 3 of the 4 companies, the duplicates were reasonably close to each other, but the individual tests were far apart. And one of the companies, the individual replicates was 20 years apart. So to me, and some people will say, but maybe, the True Diagnostic test is great and the Elysium test is terrible, or the Tally Health test is terrible and the other one is great. Maybe, but how do we know? So my sort of take home is that the direct-to-consumer biological age testing industry is a complete mess. And I have no idea who to believe or if any of them are actually giving accurate data. I know some of the people at some of the companies, and I have my personal feelings about who's trying to do it right and who's sort of a charlatan, but across the industry, it's really hard to know. So the last thing I'll say on this is where I've sort of landed is I think these are really good research tools. I think the direct-to-consumer component has gotten way ahead of itself, and I think I align with what you were saying about the way you think about these tests. Is I don't think there's a lot of value in clinical practice right now because we don't know precision or accuracy, and I don't think you can make actionable recommendations based on these tests.
Furthermore, they fail in the one thing that I think they're attempting to do, which is, and I usually use this illustration with patients. So if I have a 40-year-old patient who says, I really want to do one of these tests, I say, if the answer comes back and says you're 20, is your expectation that you will live another 70 years? Conversely, if the answer comes back and says 60, is it your expectation that you will live another 30 years? In other words, is this number predictive of future years of life? Because right now we have this thing called chronologic age that is the single best predictor of future years of life. So do we think biologic age as determined by these tests is better as a predictor of future years of life? Which, by the way, would be very testable. Like, how many people have contacted you to get ITP sample data to say, can we predict how much longer these mice were going to live?
The answer to the question is obvious and very well known. You can tell if you have your 40-year-old patient and he or she is fat, doesn't exercise, eats mostly cheeseburgers. You know that their life expectancy is probably not as good as the 40-year-old patient in your next waiting room that has extremely healthful habits and whose parents live to be 100. So and there's tons of published
but I don't need a biologic age to tell me
Right,
that.
that's what I'm saying.
Yep.
There are tons of things you can measure on individuals. 4 or 5 of them are all you really need to ask of a 70-year-old.
Yeah, MetLife does this really well.
Because their buddies on the line there, they're running life insurance policies, right? So it's not at all hard to figure out a very small set of tests that tell you how long a 70-year-old is likely to live. There's nothing to do with methylation clocks or things like that.
To me, that's the gold standard. When life insurance companies start using biologic clocks as the cornerstone of their actuarial algorithms, I'll start to be
I don't think we're that
impressed.
far away from that, though. Again, I'm going to sound like a broken record here, but you guys keep saying biological age when what you mean is epigenetic age or epigenetic tests.
Not necessarily.
Right?
And we should explain to people that there is a difference because so some of these clocks use solely epigenetic measurements.
Most of the direct-to-consumer ones are epigenetic tests.
But some of these tests use a litany of biomarkers inclusive of epigenetics.
Yes.
So they'll say, we've sampled your methylation pattern, but we also looked at your vitamin D level, your glucose level, your cholesterol level, and a whole bunch of other things, and we compressed all of that into a number as well.
So I guess let me frame it as a question to you, right? So let's take the epigenetic piece out. Again, I do think we will get to a point where the technology is developed far enough and the quality control is good enough on the consumer side that these tests will be better than just chronological age.
Yep.
But so you've got...
Sorry, you're saying...
I think we can get there. I think
that's a big statement. I don't know that I'm disagreeing with you. I just want to make sure we understand the statement.
I think it's clear from the research, unless you think that all of the research that's been done on these epigenetic aging clocks is somehow flawed, it's clear that you can create algorithms that can predict specific methylation patterns that are more highly correlated with life expectancy than chronological age.
But I think the big but here is that even if that's the case, they would not be as good as what Peter would predict after all the tests that you run your
biological age.
Through. That's
what I want to get to. Yes. Yeah. And I think what you are actually doing is looking at other biomarkers that have a long-term clinical history that you're using to come up with a surrogate, but really is reflecting largely biological age. Maybe not completely. And this is the other point I wanted to make is I don't think biological age and health are equal. I think they're strongly overlapping. And certainly you can identify many ways to reduce health without accelerating biological aging, right? I think that's easy, right? We can all think of ways to do that. So let's take a minute and try.
Yeah. So let's think about this for a second. I have seen very impressive data where we can look at tissue samples of organs and we can tell, okay, I'm going to show you a sample of nephrons. And we just based on nothing but the methylation pattern, we know that if I just said to you, one of these is a 20-year-old, one of these is a 50-year-old, and one of these is a 70-year-old, it's very easy to predict based on the methylation pattern which nephron came from which person. Completely agree with that.
Yeah, I mean, there are a lot of things that change with age. The literature has 25,000 things that change with age. Average amount of methylation at these 10 spots is number 11,407 of those. So great, you've got another thing that changes with age.
So that's the question,
But that's
Matt.
not enough.
Right. So do you believe that all of the research we're seeing on the epigenetic clocks is going to be the 78th variable that we would include in our gestalt of?
I don't know. Yeah, it's a good question. So I am hopeful that epigenetic algorithms can get to the point where they can replace many, certainly not all, but many of the other biomarkers that are being measured. I think the thing that gives me hope is we know that epigenetic changes are part of biological aging. This again is a different question, but if we look at the hallmarks of aging, epigenetic dysregulation is one of the 12, right? Some people will argue it's the most important one. That's a different conversation, but it's at least part. So that gives me some hope that we are in fact measuring something that plays a causal role in the aging process. And I think what's missing, I think what would give all of us a lot more confidence is if we had a mechanistic connection to the specific methylation changes and some cause of aging or age-related disease. In other words, this change in methylation changes this particular gene's expression level, which changes the rate of biological aging, right? I think if we had that, we'd feel a lot more confident.
Yeah, you and I spoke about this very briefly at the end of our last podcast, and I want to come back to it with all of us on this table, right? Which is, because there's so much in what you just said, Matt, that I'm gonna lay out a broad question, and then we can start attacking it in different ways. So one of the things I want to address is, do we believe that it's possible that of the hallmarks of aging, epigenetic change is the most important? Another topic I want to address, do we believe that the epigenetic changes that we observe over time, which are undeniable, are causal in the arrival of other states? Everything from the arrival of senescent cells, the increase in inflammation, the reduced function of the organs, which really is the hallmark of aging. And if so, does that mean that reversing the epigenetic phenotype will undo the phenotype of interest? And Rich, where I'm going that you and I left off was, what about the proteome? What about the metabolome?
So you made three statements there, broad, general statements. And I think each of the three deserves careful amendment.
Let's do it.
To be polite about it. The first has to do with hallmarks of aging, which I think set the field back dramatically. I think when you are officially branded a hallmark of aging by two people sitting alone at their computers and writing a review article, a hallmark of aging.
Wait, I thought they were walking around a pond when they came up with this. All right, okay.
Means that somebody once said, I'm interested in aging. That's kind of important, isn't it? Let's put it on our list. You can't tell if something is a hallmark of aging. Does that mean it goes up with age? It goes down with age? You can change it in a way that will extend lifespan. You can kill a mouse or a worm by removing it. It's something that somebody once thought might be of interest to aging. And the downside of that is once you're officially branded as a hallmark of aging, anyone who wants to write a grant on that doesn't have to prove that their fundamental cause and effect model has any merit because it's a hallmark of aging. I don't have to prove it anymore. Someone, I don't know who or on what grounds, has decided it's important. My reviewers know it's important because they've read the hallmark of aging paper, so I don't have to think about whether it's important. The negative side of that coin is that there are lots of things that didn't make it into the hallmark list And I really think it's premature to close thought off on some of those. It's easy to come up with a dozen things that ought to be investigated, but if you want to investigate it and it's not on the hallmarks list, what are you wasting? So deciding which of the hallmarks is the big daddy hallmark or whatever strikes me as not the correct thing to talk about in the hallmarks arena. The second question.
So maybe we should talk about that before we go through all this. I think there's a lot to unpack there.
You'll remember the other ones too.
If you guys could afford to give me a little piece of paper and a pen, then I'd be able to write down.
I think the hallmarks is a list, a kind of arbitrary list, not completely arbitrary, because they had some reasons for being there. And I don't think any of us would say that those 12 things are not involved in aging. But that's a very little interest.
Do any of us want to rattle them off, being that I'm the only one that's got the list sitting in front of me?
We could do a game where we each name one and see who can't.
See if we get to all 12.
Yeah.
But certainly in that list, I would not consider epigenetics as the key hallmark. Assuming there are such things, I consider it to be an interesting list. It became biblically sacrosanct almost immediately, and I've never understood why, but for some reason it did. So I'd agree with Rich.
So conceptually beautiful. I mean, so I agree completely with Rich, and he knows I do because we've talked about this before. And I think the flip side is I think the hallmarks have been immensely useful to the field. They are a very easy way to communicate this idea of biological aging, and it helps convince some of the scientific community that thought it was all just hocus pocus and snake oil that there is some mechanistic research happening. We can point to specific things that are aging. So I think that part of the hallmarks has been actually really valuable and has contributed to the popularization of longevity, and at least to the extent the science of longevity has been popularized, has contributed to that. And it has been extremely detrimental to the field. And the way I think about it is it just caused the field to narrow prematurely. And this goes back to what I alluded to before. I don't know if we understand 80% of biological aging or 0.005% of biological aging. My guess is it's closer to 0.005%. And by and large, the funding to look outside of the hallmarks dried up once the hallmarks became the dominant paradigm and people stopped looking. And I think we need to go back to more discovery science and thinking outside the box. So I think it's been a double-edged sword.
Would that happen automatically if we could wave that magic wand and increase funding?
It would help. I don't know that it would help enough, but it would help. I think you also kind of have to change the mindset about what people call fishing expeditions. That's like a bad word in grant review panels. Fishing expedition, meaning you don't really know what you're going to find, but you got to go look before you can figure out what's important. So I think we have to kind of change that mindset as well.
One can usefully concretize this discussion. I imagine that I don't read these papers because they upset me, but I imagine inflammation is on one or more of these
sure
lists.
Is.
I'll bet. So
chronic inflammation.
Okay, good. Chronic inflammation. So
I like that one.
What that does is you say, I'm interested in chronic inflammation, so I'm doing good stuff, huh? But what could be happening is this particular set of cytokines might be overexpressed by some glial cells, and that leads to loss of cognitive function, whereas this other overlapping set of cytokines produced by the macrophages in your fat may make you more prone to diabetes or metabolic syndrome, whereas this particular set of lymphocytes are necessary to repel COVID, and that's why you are more susceptible to COVID. So learning what changes within the extremely broad generic idea of inflammation, what changes in what cell types, in what people, under what pharmacological or genetic changes, how they are interacting with other aspects of pathology, that's marvelous to do. But to say, inflammation, that gets bad when you're old, is a way of avoiding the labor of thinking. And that's why I'm against it.
And I think Matt brought up a really important point, and we scientists are to blame, is the way that research gets reviewed. And for lazy reviewers, having these 12 hallmarks is really helpful. This has got one of the hallmarks in it. This must be good stuff. I do think reviewers need to be more open to new ideas and new approaches. I mean, everybody knows that NIH grants are approved if they're incremental. If they're really breakthrough, they don't get approved. In fact, A very famous biologist, E.O. Wilson, told me years ago, he said, don't ever include your best ideas in a grant. They won't get funded. Do standard stuff. Save your best ideas for projects that you do on the side.
Yeah, that's one of the reasons I left academia. It drove me nuts. Almost impossible to get the important stuff funded.
So what's your second?
I wrote them down.
Let's go back.
So the second of your multi-partite question was, does epigenetic change, what are the results of?
Is it causal?
Causal effect. And the third, which we may get to, is can you reverse it, and would that be a good thing? So let's talk about the second element here, is it causal? And the problem is what it means. There are some changes that occur in this particular set of 40 cells in the pineal. And there are other changes that occur in these cells in the bone marrow, and there are other cells that change in the gut and villus lining cells and the crypt cells. So they are all epigenetic in some. They are caused by some things. And we don't really know which, if any of these, count for aging. If someone says, I'm going to prove that an epigenetic change is responsible for aging, they haven't begun to come to grips with the nitty-gritty. People always ask, just as you hinted, does your drug change epigenetic things? And unfortunately, that's where they stop thinking. If we're always willing to give people tissues from our drug-treated mice if they are keen on epigenetic changes that affect neuron regeneration, excellent. Their experts will send them the brains and they can do that stuff. It's important. I'm not making fun of it. But the general notion that it's aging vaguely thought of is due to epigenetic change more vaguely thought of doesn't really get you anywhere. That's my sort of skeptical view.
And is part of the issue that you're saying, well, what's causing the cause?
No, it's just that the concept of epigenetic change encompasses thousands of changes in hundreds of cell types under hundreds of influences. Of course, some of that causes other stuff. Agreeing to that, assenting to that notion that epigenetic change is causal for all sorts of age-related pathologies, everyone can agree to that, but it's meaningless, because what counts is to say this specific change is really important in this disease.
But let's go back to the example I used.
Here's an epigenetic alteration, or this specific broad spectrum change in multiple tissues causes something good or bad. You have to define what it is before you can test it.
So let's use a specific example. When you look at a patient with type 1 diabetes and you look at their beta cells in their pancreas, they look different epigenetically than the beta cells of an age-matched person without type 1 diabetes. Okay. And we also know that their beta cells don't function. So they've lost function. Yeah. So let's ask that question as a specific example. What do you believe, or what confidence would you assign to the notion that the epigenetic change on the beta cells of the type 1 diabetic are indeed causal to the loss of function of the beta cell?
Right. So my last exposure to the causes of type 1 diabetes was when I was in medical school, which is more than 5 years ago. But if I vaguely remember, it was an autoimmune disease, right? So if your poor little helpless beta cells are being attacked by antibodies and macrophages and things, those stress reactions are going to cause epigenetic change. And whether those epigenetic changes contribute to some extent to the ill fate of the beta cells, it's possible. And if I were an expert on diabetes pathogenesis, I'd really want to know that. It doesn't have anything to do with aging, but it's an interesting question.
But it's a way to address causality.
Yeah,
you might equally say, no, it's the mitochondria that have changed.
That's right.
Why would be the
a hallmark of diabetes?
Yeah, or it's the glycated proteins, misfolded there's a ton of things, and there's no reason in the world at this stage, I think, to actually give epigenetics primacy over anything.
And then it's a nice hypothesis, right?
Diabetes is well known.
You
you can formulate these questions because a lot is known about type 1 diabetes. And I understand 0.05% of the biology of aging.
0.05, yeah. You're off by an order of magnitude.
I'm tenfold off.
He was raising you by a log.
Yeah, I thought you're one log off. So formulating the questions in exactly the way Steve did makes it clear how difficult it is to evaluate the concept that epigenetic change contributes to pathogenesis in type 1 diabetes. and we know more or less what is going on. We don't know what's going on in aging. We don't even know what part of the body it's going on, or parts more likely of the body.
I at least internally reframe it a little bit and say, what would the experiment be? What would you need to do to convince yourself that either, broadly speaking, epigenetic dysregulation causes aging, whatever that means, or this specific epigenetic change that is associated with chronological age causes aging, right? And so that's an easier way for me to think about it, because I feel like it's all a fascinating conversation, but we're never going to get to the answer until somebody actually does the experiment or
decides that it can't be formulated because it's too complicated and gives up.
Yeah, that's right. But people are trying to do both of those things.
Right,
I mean, people are using partial or transient epigenetic reprogramming and asking, can that have effects on biological aging? I'm actually cautiously optimistic it can. I don't think it's going to be a game changer, but I think you can modulate aspects of biological aging. And then people are, the technologies are being developed for targeted epigenetic modifications. So if we think this particular epigenetic mark at this particular location in the genome controls aging, and I don't think it's going to be that simple, but let's say it is, you could go in, you could modify that and then see, do you reduce disease? Do you increase lifespan? Do you improve health span, right? So those are the kinds of experiments that I think would get us to where we can have a lot of confidence. If it's the case, if somebody, let's say at Altos, publishes a paper 3 years from now that they have made a mouse live 6 years by multiple rounds of transient epigenetic reprogramming, I'll be like their biggest fan. They moved the needle. That convinces me that that strategy modulates biological aging. Nobody's done that yet.
What about something far less impressive, but still worthwhile? So consider, if we could get to the point where we could locally deliver vectors that would epigenetically change chondrocytes so that you could take osteoarthritis in the knee and just regenerate cartilage,
clinically useful
by changing the epigenome.
But is that biological aging, right? I wouldn't be convinced that's modulating the biological aging process. I would be convinced that's a clinically useful strategy for people who benefit from that therapy.
I guess it kind of depends on why we think an individual would be experiencing osteoarthritis, right? How much of that is senescence? How much of that is inflammation?
You're trigger Rich here before we go down that path.
Is it the S word or what?
Yeah. Let's talk about senescence. But
if you think osteoarthritis of the knee requires a knee joint replacement, and that's going to help your patient, you are not rejuvenating. It's perfectly possible to do great things with technology, including chondrocyte regeneration, without having to decide that that's related to aging. People don't age because they fail to have titanium knee joints or something.
And one way I think about this, and again, this may be completely wrong, but it's a useful way for me to think about it, is I think about age-related disease as the sort of downstream effect of biological aging. And then for most diseases, there becomes a point where the pathology of that disease mechanistically is no longer the same as biological aging.
He's very good. You should listen to him.
And one of the implications of that is the interventions that slow biological aging may not work once you get past that point, but things that do work for that disease may have nothing to do with biological aging. Does that make sense?
Yeah, go deeper on that idea though. Let's use the example.
Yeah, well, I think, so what's your favorite disease?
My favorite disease. Let's talk about cancer.
Cancer's an easy one, right?
Let's talk about cancer.
We know with cancer, in many cancers, the process is you have one or more mutations, which then often lead to additional mutations. You get genome instability. Eventually, you get an oncogene that gets activated, and that leads to uncontrolled cell division. There are more
tumor suppressor gene that gets deactivated.
Right. Yeah, right. So and if we accept that immune surveillance is one important anti-cancer mechanism, we know that immune surveillance declines with age. So early on, we're clearing a lot of our cancers. As our immune system declines, these cancers are going to escape immune surveillance. They're going to accumulate all these mutations. They're eventually going to go into uncontrolled cell division. That uncontrolled cell division, at that point, you can treat the cancer, right? But uncontrolled cell division is not biological aging. Right. It's not a normal part. It's not a part of the normative aging process.
That's right. Yep.
Right. So the treatment there, So the mechanism now is fundamentally different from normative aging. And the treatment, let's just say the treatment in this case is chemotherapy, might benefit the cancer.
It has nothing to do with targeting.
Aging, right? And I think rapamycin's a good example here where I think we all believe that rapamycin and inhibiting mTOR slows biological aging, at least in up to mice, hopefully in dogs, hopefully in people. Yeah. So it's a fundamental node in the network. That's the way I think about the hallmarks of aging. It's a node in the network that underlies the hallmarks of aging. So we can manipulate mTOR with rapamycin, slow aging. Rapamycin's a pretty good anti-cancer drug until the cancers have evolved to ignore the mTOR break. And then rapamycin doesn't work anymore. And we know rapamycin doesn't work for most cancers. That's an example.
That's been tested. We know this.
Yeah, absolutely. Yep. And it's because the cancers evolve to bypass the mTOR break or to bypass the ability of rapamycin to inhibit mTOR. So that's a case where the intervention...
That's a really good point that we all take for granted that I think is worth noting. Rapamycin can be unsuccessful as a chemotherapeutic agent and can yet be very successful as a cancer preventive agent.
Absolutely.
And it's exactly for that reason.
Yeah. And I think this also illustrates why traditional disease-based medicine is not about the biology of aging. It's about something else. The biology of aging is distinct and it needs to be investigated in a different way. And we know that in the aging field, but the people in the cancer field and the cardiology field and the neurology field, I don't think they understand that.
Well, so this gets to what I wish if I were health czar, this is what I would do. Because, it comes back to what Rich said at the outset, which is, why is this a zero-sum game? You didn't ask it that way, but that's effectively the problem you're dealing with, right? Which is, why can't we study cardiology, oncology, and neurology and aging without everybody feeling like they're taking it? My way of saying that in Peter terms is we need to have medicine 2.0 and medicine 3.0 in parallel, because the tools of the medicine 2.0 scientist and physician, which we see on display today, are putting the stent in, giving the chemotherapy, lowering the cholesterol, all of these things. The medicine 3.0 toolkit looks different. Different science. You're going to use rapamycin here. You're not going to use it over here because it's too late. And instead of saying one or the other, why isn't it both? Why wouldn't we want both of these running in parallel?
Well, we would, but of course, the zero-sum game is a pretty good analogy for what's actually going on. The amount of research dollars, at least available to NIH, is not infinitely expansible. It's set by a complex political process. And then there's a separate downstream process that allocates it amongst institutions. So saying that it would be a good idea to have more funds, I agree with you, and I'll bet these two guys do as well.
Yeah, I think I misspoke. It will be a portfolio reallocation. But it will be worthwhile because the burden of this disease will be lower. So in other words, it's okay. It's sort of like saying, right now I spend $100,000 a year on the barrier to my house. To prevent anybody from breaking in. And I spend $100 a year patrolling the neighborhood to make sure there aren't too many bad guys in the neighborhood. There's a scenario where if your total budget is $100,000 and $100, maybe you could spend $80,000 in total by spending more money patrolling the neighborhood,
I think
less money.
We generally agree with you that having a greater proportion of available research dollars, both private and public, going into the biology of aging and its impact on late life health would be a good thing. I don't think you're going to get an argument here.
But I also think you're going to get a huge argument from anybody in the cardiology field, the neurology field.
Or Alzheimer's.
That's the Alzheimer's field. That's
it's their money.
But wouldn't some of those people, as the funding dollars move towards the aging side, also want to move and say, look, I'm going to study this through the aging lens?
I was on the council for the National Aging Institute for 3 years, and if at any point, I can swear to this from personal testimony, somebody would say something like, I wonder if maybe a few percent of the Alzheimer's budget might instead go to studying how slow aging models would have an impact on late life neurodegenerative disease. The next day, the director of the Aging Institute would get a call from 2 or 3 Congress people who were on the Appropriations Committee stating that this will not be happening because there was an Alzheimer's Association person who got the call from the NIA staff member in charge of Alzheimer's saying, tell the congressman to call the director and let's put a stop to that reckless idea. So they're tied in to the political process in ways that.
Well, we just need to go maybe one step further because those Congress people have a boss. They report to somebody too.
Who would that be at this stage? Sorry.
Yeah, no, I mean, come on. Maybe it's because the public doesn't understand this. But those people answer to the public. These are our dollars.
That's right.
That are going to work.
I'm with you.
But Alzheimer's Association, I mean, that's a patient advocacy group, right? So that is the public.
Yes, although let's ask the question, what have they done for those patients lately?
That's a different question. But I mean, I'm just reinforcing what you said. I think part of this is educating people.
If you know somebody who's suffering from Alzheimer's disease, you know very well that the only thing we've got going for us right now is prevention, right? We don't have too many silver bullets in the treatment gun.
Despite massive spending on it. I was once in Congress trying to lobby with about 6 people from the Alzheimer's Association in the same room, and I was totally ignored by the staffers that were in there.
I agree with all of this. I think again though, we should be careful not to demonize people for wanting to cure Alzheimer's. It's a good thing. It's a good goal. I think the communication piece is about the fact that it's going to be much more efficient and effective to keep people from getting it in the first place. This goes back to the idea that once you've outpaced the biology of aging with the pathology of the disease, it gets a lot harder to do anything about it. And so I think that communication part, I don't know why we've been so unsuccessful, because I think a lot of us have been out there trying to communicate this message for a long time, but it's starting to permeate. Again, we're at that moment, I think, where people are starting to get it, that biological aging is a thing. It's malleable. We don't really know for sure what works in people and what doesn't work yet, but we're getting there. So I think it's going to take a little while, but there's reason to be optimistic.
And there's also the private sector is another reason, I think, to be optimistic. Yeah. So let's go on record right now. I think if we defeat Alzheimer's disease, it's going to be because of the biology of aging. It's not going to be because of the drugs that get rid of, A-beta.
Absolutely. Yep. Probably cancer, probably heart disease, although I think Peter's more optimistic we can prevent heart disease through other mechanisms.
Yeah, Medicine 2.0, if you took the tools of Medicine 2.0 and just applied them 30 years earlier, we wouldn't have ASCVD. That's the one place where it's worked. But again, that's because the mechanism of action is so well understood with ASCVD compared to Alzheimer's and cancer.
A lot of infectious disease, a lot of liver disease, a lot of kidney disease, all of those things can be improved dramatically by targeting the biology of aging.
If I were to write my book again, I would add a 5th horseman, because I talked about these 4 horsemen of ASCVD, cancer, neurodegenerative and dementing diseases, and metabolic disease. But I would actually add a 5th sort of hallmark. It's not really a hallmark of disease, but it's kind of the 5th thing that brings life to a bad close, which is immune dysfunction, right? Mm-hmm. And I don't think I gave that enough attention in the book because, of course, as you said, it factors in very heavily to oncogenesis. But also, I mean, as COVID showed us, what a risk factor it was to be old.
Yeah.
And, I'm reminded of this when I see people my age get brutal pneumonias and 2 months later, they're okay. And you realize... And you look, I mean, I've one of my patients, 2 of my patients actually in the past 6 months have had really bad pneumonias where you're looking at the CT of their chest and you cannot believe they're alive. But of course they're fine. 3 months later, 4 courses of antibiotics later, they're fine. And you realize you do that to a 75-year-old, it's over. And it simply comes down to how their B cells and T cells work. And so that's an area that, again, that to me is an area where I'd love to see more attention, which is, what would it take to rejuvenate the immune system as a proactive statement, right?
Well, that's part of the X Prize healthspan challenge, of course. I think that's a perfect example. Influenza pneumonia has never fallen out of the top 10 causes of death in the U.S. It used to be number 2, but still now it's number 8 or 9. But it's always there because you can't really do anything about the late life immune dysfunction. So
I want to shift gears
and so one can, just to follow this up, and so if magically you become in charge and you're able to double the amount of research being done on the biology of aging fundamentally, then we can afford to do, let's give some mice, to start with, a batch of anti-aging drugs and see if it makes them more resistant to infectious illnesses, including pneumonias, but viral infections as well, and many others. I'd love to know the answer to that, and no one has actually really looked in a serious way, because the ITP has enough money to just measure lifespan,
right? None
and
of the
we're
healthspan
hoping
issues.
that everybody else is now going to look at the brain and the lungs and the infection and the sensory systems. That really ought to be done, and it's not being done because of a lack of money.
You said something a while ago, Rich, that I think is timely now, which is, with each generation of these drugs, they get more efficacious and less toxic.
Not yet, but that's the hope.
Well, no, but I'm going to use another example.
Okay.
The GLP-1s are the best example of this, right? So you go back to the very, very first generation of GLP-1 agonists, barely lost any weight, horrible side effects, right? Generation 2, about 10 years ago, a little bit better weight loss, side effects so-so. Fast forward to semaglutide, quite a bit better efficacy, still really bad side effects. Next generation tirzepatide, better efficacy, side effects are almost gone. Yeah. Now, why haven't we been able to do that with these geroprotective drugs? So we have this one study using everolimus that gives us a hint that says, hey, this might actually enhance immune function in people in their mid-60s. But we need the follow-up study, the follow-up drug. Imagine what the fourth generation of that drug can do, where it's tuned to get better and better and to have fewer side effects.
Commercial motivations. You know, you're going to sell a lot of the obesity drugs. There are very strong commercial motivations to do those studies over and over and over again until you find one that works better. And they're good preclinical models that you can use so that you're not wasting too much of your time on clinical trials. That could be done for anti-aging drugs as well, although testing anti-aging drugs in people is a whole separate set of tangle of difficulties. I don't want to talk about that right now, but I'm saying it won't be quite as easy as it was for anti-obesity medications. But no one's doing even the first level of research to find the optimal compounds for efficacy without side effects, or even to begin to see if they have desirable effects on aging rate indicators in people. That's kind of a cheap and easy study, and no one has really tackled that yet.
Well, I just heard that there are over 80 senolytic studies in early clinical
trials. No, I meant
trial
anti-aging drugs.
Yeah, well,
it's a joke. It's a joke.
I mean,
it's a joke. It's a joke.
We have to come back to this.
Are any of them powered for anything other than safety? This is, I think,
it's
the problem.
all phase 1 at this
exactly.
point.
So they're underpowered. They're almost useless, in my opinion.
Well, until they get to phase 2, phase 3. If they get
how
there.
many years have we been having phase 1 senolytic trials now?
I don't know.
At least a decade.
God, has it been that long? First one I remember was 2017. So yeah, a decade easily, because I probably wasn't paying attention in 2014, 2015.
So yeah. Anyways, there's lots of complicated issues here. I think endpoints for clinical trials are really challenging, but solvable.
So there are two places I wanted to go next, and I'm going to let Rich decide, because he's going to have the strongest point of view. Can we talk about senescence, or can we talk about what biomarkers would be necessary to help us study aging in humans as we translate from your work and Matt's work?
I know what I want to talk about, and it's the second of those two.
Okay.
I don't want to spend the next 3 or 4 hours explaining why senescence is silly and anti-senolytics are untested at best.
So there's no way we're not talking about that, but very well. Let's go on to item number 2.
And I think the most important thing is to make a clear distinction between biomarkers and aging rate indicators. So
please explain the difference to people, please.
Okay, I'll do my best. So a biomarker, allegedly, and in real life, is something that changes with age. So if you have some drug that slows aging, the biomarkers, many of them in the different cell types and in the blood will change more slowly. They are a good way of looking at whether you're slowing. It'll work in the dogs. Long-lived dogs and short-lived dogs will have differences in the rate of change of biomarkers. Very established part of the literature and valuable. But you have to wait till somebody's old, whether it's a dog or a mouse or a person, because only when they're old has the biomarker of aging, the surrogate marker for biological aging, changed very much. So in a clinical trial, certainly in a human situation, no one wants to wait 20 years to see whether the biomarkers have changed. And 1 year is such a tiny fraction of a human lifespan that you don't really anticipate detectable change with an appropriately powered study. It's like aging rate indicators, which are much less well studied and much less well established in principle, are things you can measure that tell you whether you're in a slow aging state or a normal state.
Can I just make a point for the listeners so they understand kind of the challenge of what we're talking about?
Yeah.
When we study blood pressure drugs or cholesterol drugs, the biomarkers change so rapidly, and we know the relationship between the biomarker and the disease state. Mm-hmm. So if your blood pressure is 145/90 on average, before I give you this ACE inhibitor, and 3 months later, 6 months later, 9 months later, a year later, your blood pressure is averaging 119/74, I know I've done something well. Now, I will still probably in the phase 3, in fact, I will in the phase 3 have to make sure that I also reduce some event in you. Yeah. But generally by the phase 2, I know that this drug is not toxic and that it's predictably lowering your blood pressure. That's really, really valuable.
A biomarker generically is something that's easy to measure, that is informative about something that's hard to measure. A classical example, famous example, is you want to know how many cigarettes somebody smokes a day, they'll lie to you. But if you measure cotinine in their blood, that's a byproduct of nicotine. You don't have to ask them. You can find out how many cigarettes they had in the last couple of days by measuring blood cotinine. That's a biomarker of cigarette consumption.
Is it a marker of nicotine or carbon monoxide?
I don't know the answer to that.
I wasn't sure.
So in principle, a biomarker of aging is measuring, there are many of them, and they are measuring biological aging processes, and they're useful in that regard. But they don't tell you how fast you're aging. The analogy I love to use is an odometer is like a biomarker of aging of your car. It tells you how many miles your car has gone, but it doesn't tell you how fast the car is going. The speedometer tells you how fast your car is going. And so what we need, and what I think we're just beginning now to document, is things like the speedometer, aging rate indicators that reliably discriminate slow aging mice or people from regular old mice or people. We have now a dozen or so things that change in the fat, in the blood, in the liver, in the brain, and in the muscle that are always changed in any slow-aging mouse, whether it's drug A, drug B, drug C, calorie restriction diet, or single gene mutations. We've looked now at 5 different single gene mutations. And this whole set of 12, or roughly 12, aging rate indicators always changes in every slow-aging mouse, and it does so in youth, which is the key point. So if it does so quickly after an anti-aging drug is administered, that's the transition, that's the bridge you need for clinical studies in people. If you want to know whether Metformin or Canagliflozin or something slows aging in people, and you don't want to wait 20 years, but you've got things that tell you whether they're in a slow aging state, how fast they are aging versus normal. And that's a big if. We don't yet have evidence we can do that. We just have hope we can do that. Then that allows you quickly being within 6 months to a year, to know whether your anti-aging manipulation, alleged anti-aging manipulation, has moved them to a physiological status which is associated with slower aging. That can be done. A lot of that can be done in mice with drugs, with mutants.
And are these all proteins, Rich?
No, some of them are changes in the fat, different classes of macrophages. The pro-inflammatory macrophages, the bad ones, go away. The anti-inflammatory macrophages, the good ones, go up.
UCP1, I recall from our discussion.
UCP1 goes up in every one of our 10 different kinds, 11 now, of slow-aging mice.
Does it go up in any of the mice that did not receive a successful drug?
Well, we compare them to controls. And the question you're asking is really important. That's what we're doing in the next 5 years. We just got a grant to do that. We're going to take mice and give them either a good drug or a different drug that doesn't work, and then make those comparisons. It's a really important thing to prove. So far, our only control has been untreated mice.
At some point in this, I had to bring this up. But let's imagine that Rich is incredibly successful at finding these things. That is a very, very long way from assuming that it's going to be the same in people. Most things that clinically work in mice do not work in people. It might be, and that would be wonderful, but I think ultimately we're going to have to find this for people. And my thought is the kind of evaluation that you do routinely of your patients. If we took a group of 65-year-olds and we gave them a drug that we thought was an anti-aging drug and followed them the next 5 or 6 years doing these evaluations, I think you could probably safely say this is slowing aging or not slowing aging. So I don't think that it's going to be that easy to jump from mice to people in this.
I've always wondered if in people the easiest way to do it would be to take the most obvious thing that we know is going to reduce the rate of aging. So it'd be an interesting experiment, but you find someone who is overweight, diabetic, and smokes and has hypertension. You get hundreds of these folks. You put half of them on a sort of, to be ethical, a plan where you try to get them to stop, and presumably many don't, right? But in the other group, you pull out all the stops. And you don't care because you're interested not in testing the hypothesis, does this thing help you? You're interested in getting them to lose weight, not have diabetes, stop smoking, exercise like crazy. So you have the greatest division between two groups of individuals where we would, I think, be able to agree that this group is now aging slower, the group that we've reconciled their diabetes, quit the smoking, et cetera, et cetera. And then I'd love to see Rich's 12 line up in that population.
That would be great. Let me just say that I think that people that study animals, myself included, always underestimate how well we can evaluate health in people with a very, very thorough evaluation, because we don't do that in our experimental animals.
Why do you think that is, Steve? Why is it that... Because I was going to ask about parabiosis later on in the discussion. We might as well talk about it now, right? Parabiosis seems to actually kind of work in certain mouse models. Do we have any reason to believe it's going to work in humans? And if not, why not? Why are mice so different from people?
Well, wait a minute. I wouldn't say that just because we don't have evidence that it works in humans means mice are different from people. First of all, when it comes to parabiosis, right? I mean, that's a different discussion. But I actually have a little bit, I agree that most, if you look at the attempts to cure cancer or other diseases in mice and translation to people, most have failed. I actually think that's because those are artificial mouse models where they tried to give young mice an age-related disease. I'm more optimistic.
But Rich's are not.
I don't know this.
Rich doesn't have those mice, yeah.
I know. I'm more optimistic that biological aging or normative aging is going to be much more likely to translate to people, both interventions and biomarkers, than the specific disease interventions. I might be wrong. I don't know the answer. I'm just more optimistic.
We would hope that's the case.
Yeah. So I don't.
That's fair.
I don't think we should rule out the mice as a useful model. In fact, I think there's reason to be optimistic that it will. I actually am kind of bullish on parabiosis as, like, I think it will work to some extent in people. It's not a pragmatic approach for population gerotherapeutics.
But I'm just wondering, like, why it wouldn't be as efficacious.
How do we know it's not?
Yeah, right. This is something that, I mean, aren't there 6 or 8 clinical trials going on right now?
Different variants of that,
yeah.
So I haven't seen them. I've seen the one that's looking at, well, there's the one that, it's not really a parabiosis study, but it's looking at plasmapheresis for Alzheimer's. But I consider that a little bit different, but fair enough. Okay. Because they're just using albumin, I think, aren't they?
Right. But there's also studies going on of young blood.
Yeah. Okay.
Right? So,
But if you think of parabiosis as both, taking away the bad stuff that accumulates with age and adding in the good stuff that's in young, some sort of plasma exchange hits at least half that equation, right?
Okay. Let's go. I want to come back to this, but so my question was, why the difference? You're saying, Matt, The difference is probably amplified in disease-specific cases like heart disease, cancer, and Alzheimer's disease. Probably less relevant when you're talking about aging, because even a flawed mouse model still ages. In fact, it's designed to age in a certain way.
Yeah, and I mean, I think normative aging looks very similar. Again, if we look from mice to dogs to people, just sort of broadly speaking, the process looks pretty similar. So I'm cautiously optimistic that these things are going to translate.
I think the reason that, not to pay too much attention to Steve's pessimism on this point, although he's completely right, of course, most things that do have an important effect in mice fail in human clinical trials. And it's for a variety of reasons. Sometimes humans are different from mice. Sometimes the drug has side effects that are tolerable in mice, not tolerable in people, etc. But I always like to look at the other side of the coin. That is, if your goal is to develop a drug that blunts pain in people, and you screen 40 or 50 drugs and you find a couple that inhibit pain in mice, that's a really good start. It doesn't guarantee they're going to work in people, but it gives you this category of snail-based neurotoxins. Let's make 40 of those from 40 different snails. We'll find one that actually in people works, can be made by a scalable process and doesn't produce serious side effects. So the mice are not it's not a one-to-one mapping. It works in mice, it works in people, but it's an important critical first step, which usually succeeds in finding a set of drugs of related families, or with related targets at least, that are efficacious in people. Most drugs that are used in people had useful rodent-based research somewhere in their pedigree.
And I absolutely agree with that, Rich. And nobody's saying that 100% of things that work in mice do not work. But I think there's a critical difference for aging research, which it takes 4 years to do one of these in mice, right? And so if we have to do 40 to find one or two that work,
that's why I like aging rate indicators, speed things up.
So let me ask a question. I'm sorry, I'm stepping on your toes, Peter, but the question I always come back to, I agree, we need these aging rate indicators. How do we get to the point where we're confident that they actually work in people? And maybe more importantly, how do we get to the point that FDA is confident that they work? Because that's the only way you're going to be able to use them in a clinical trial. And I don't see a path in the short term.
Well, I don't know that we need that, to tell you the truth. So I went to the FDA to try to get them to approve a trial of Metformin. And we didn't couch it in aging, because you're right. As soon as you mention aging, their eyes glaze over and they're not interested anymore. But we did it in terms of multimorbidity, and they were fine. They were fine with that.
But that's a different endpoint. That's not a biomarker.
My reply to your question is that you've merged two different difficult problems. Problem A, can we find drugs that slow aging in people? Problem B, can we surmount the legal and political barriers to getting them to
That's
work?
not what I was asking. I was asking, how do we get to the point?
That's what I'm...
Okay.
What I'm saying is that you are focused on something I don't have any answers to, basically, which is how do we get the FDA to develop and approve clinical trials? I was more interested in a step before that. It would be nice to have some drugs that actually do work to slow aging in people.
But you have to trust the biomarker of aging rate before you can be confident that the drug that moves the biomarker of aging rate works in people. That's fundamentally what I'm asking.
Right. Well, that's a good.
How do we get to the point where, even let's just take FDA out of the equation, the four of us would sit and look at the data and I'll be like, yep.
Well, that's sort of my thought experiment, right? I would have to take an example in humans that is so egregious that nobody with a straight face could say one group isn't now aging slower than the others.
Sure. Would that convince you, though? So let's say we do that. Let's say
it would make me worry. It wouldn't be.
Yeah, it wouldn't be perfect.
It would only show you the positive signal. It wouldn't show you. It would show you the specificity and not the sensitivity of the test. That's the problem.
Sorry.
Well, I was just going to say you might miss the signal. If you found a proteomic, genomic, epigenetic, like if you found a multimodal signal that detected a rate of detection and a difference in rate of aging between those two very extreme sets, you might miss it with a geroprotective drug, which wouldn't be as dramatic as that change.
So what if I told you that there are people who claim there are epigenetic signatures that do that correlate quite well, they claim, with health outcomes, 10-year mortality, 5-year mortality, 3-year mortality in people, and are measuring the rate of biological aging. Because it's out there. I mean, it's in the literature.
I mean, this is not perfect, but it would be one thing I would immediately think of, which is I would take a really good biobank that would have enough samples that I could, sample a bunch of human stuff and use an unbiased sample and a biased sample. So I would determine an algorithm based on one and see how well it predicted on another based on enough samples. I mean, that would have to be true at a minimum.
Yeah, I think it is. I mean, again, I think at least it depends on how much faith you put in these research studies. But I mean, people have published epigenetic algorithms. Dunedin pace is the one that most people are going to talk about, right? That correlate seemingly pretty well, at least with mortality and with metrics of health span, for lack of a better way of framing it. So that exists.
And Dunedin pace is using something besides epigenetic, or is it only epigenetic? I think it uses something else.
It was trained off of other biomarkers, and then they found epigenetic marks that correlate with those other biomarkers. So it's a correlation to a correlation, but there's still a correlation.
What do you think, Rich?
Well, I wanted to go back to the example you gave, where you took a lot of people and gave them intense exercises and dietary changes to improve their likely health outcomes. And that's a good place to start a discussion, because you said every sensible person would see the treated group as aging more slowly. And I would want to ask, before I agreed to that, do they also have improved cognition? How are they doing in cataracts? How are they doing in hearing? What happens when you give them a flu shot? Do they have a great flu shot? So the things you've pointed to are really important for both overall health and for cardiovascular risk and the things linked to that. So it's nice to know. But to convince me that you now have a slow aging group of people, you need to go beyond the risk factors for specific common human diseases. If you could show that, then for the first time, I would be convinced you had an effective anti-aging manipulation in people. Currently, I don't know that there is any effective anti-aging manipulation in people. If your approach got there, that would be a terrific research model.
Well, but now we're getting into the definition of aging a little bit, which is, would you agree that the approach I'm describing would produce a longer life?
It's easy to produce a longer life. If you happen to have a clinical condition where you're tied to a railroad track and there's a train coming, you can extend that woman's life enormously by simply giving her a knife and cutting the bonds and letting her walk away from the track. Longevity-promoting interventions are not anti-aging.
Well, if 80% of people died as a result of trains on train tracks, that might be a worthwhile example. But given that 80% of people die from these four chronic diseases,
all in favor. I'm all in favor of protecting people against chronic diseases.
Yes.
That's a good thing, and I'm glad that people are doing that. No question about it. Now, talking about the biology of aging, there are all sorts of things that also happen when you get older that are not part of those chronic diseases. And to make a case that you've got an anti-aging manipulation, you need to show that those are changed too.
But do all of them have to change, or just most of them? I mean, I think
don't enough have to change that you increase the length and quality of your life. And if you still get a cataract at the same rate, I'm not sure that should be disqualifying.
Right. But the important thing I think about what Rich said is all the stuff that he pointed out could be easily done in humans. Wouldn't be hard to measure hearing.
The nice thing about like the dog examples, where you've got well-known, famous, long and slow aging dog breeds, and it's true for horses too, it's certainly true for mice, is that more or less everything slows down together. The tiny dogs that are very long-lived, it's not just that they have a delay of cancer, they have a delay in neurodegenerative disease, a delay in digestive diseases, in joint diseases. Aging has been slowed in those dogs.
Yep.
And if the dogs did your thing,
we might not have an intervention that does that, to your point, Rich. Well, I'm saying we might not have a non-pharmacologic method that does that. It's not clear that even though exercise clearly extends lifespan, it's not clear that it's doing so by slowing aging.
You're right.
Those are two different things, to your point.
It's not clear, but it's an interesting question. Like, do you believe exercise slows aging? Exercise, healthy diet, sleep?
I have no idea. I think so. That would be my intuition is I think so, but I can't point to the evidence that tells me so.
Well, there's evidence to support it, but it's not. The question is, does it rise to the level of evidence that would convince Rich? I don't know. I believe it probably does too, but I'm not going to, say it with 100% certainty.
I think here's where we get back into health span versus lifespan. The effect of exercise on longevity is pretty small. Its effect on quality of life is enormous.
Somewhat depends on where you start.
And it also depends on I've always found these to be a little bit problematic because I don't think that defining it by the input is as valuable as defining it by the output. In other words, to say you exercise this many minutes a week versus that many minutes a week is a little dirty because intensity matters, what you do matters. Sometimes the output is what matters more. How strong you are, how high your VO2 max is, those tend to be more predictive because that's the integral of the work that's been done. But your point is, it's well taken. Like the impact on health span is what I tell my patients. If this amount of exercise didn't make you live one day longer, the quality in which your life would improve would justify it.
Now, fortunately, we can move past this sort of semantic discussions because there's now molecular ways of checking this. Exercise, as I'll bet all of you know, increases an enzyme called GPLD1 in the blood of exercise people and in mice. And Solvieda's lab has shown that if you elevate GPLD1, it does great things to your brain, more neurogenesis and more brain-derived protective factors, brain-derived neurotropic factors. Irisin also goes up in humans and in mice after exercise. It does great things for your fat.
As does clotho?
Let's leave that out for a moment.
Oh boy. I'm striking all the nerves here today. All right.
You may be quite right. I wanted to stick with the GPLD1 and irisin to make the point that they also go up in all of the slow-aging mice. That is, all the anti-aging drugs, the calorie-restricted diet, the isoleucine-restricted diet, and 5 different single-gene mutants that extend lifespan in mice. They all elevate GPLD1.
17-alpha
estradiol?
Yes.
Canagliflozin?
In both sexes?
Well, this is the key question. For what irisin is sex-specific, GPLD1 is in both sexes. But this is how one begins to answer that question. This is the exact kind of question one has to ask. So if you are interested in the idea that exercise regimes have a benefit beyond the obvious exercise-linked physiological declines with age, do they improve cognition? And if so, how? These molecular changes are the things you need to begin to investigate. And the anti-aging studies in mice show that the anti-aging drugs, at least the ones we've looked at so far, increase the same things that exercise does.
Rich, have you done this experiment with an ITP cohort where you run, in addition to a drug parallel?
Nope.
You know what I'm going to ask?
Well, you're going to ask if we exercised our mice, right?
Yes.
Yeah, we've never done that.
So you haven't done a sedentary versus exercise?
We have not done that.
You haven't done a obesogenic versus fasted?
We never use obesogenic diets. And I mean, it's worth doing it that the ITP doesn't do. We don't have the resources. We have enough resources to test about 5 drugs a year, but if we wanted to test them in exercise versus non-exercised,
we got to get you a budget increase because that will now get to this question because now we could look at the soluble thing. Yeah.
Maybe it would, maybe it wouldn't. So I'm very
in mice.
I'm very agnostic about what we can learn from exercising mice because mice are basically kept in a jail cell, something the size of a jail cell their entire life. If you took a bunch of people and put a exercise wheel in a jail cell that would use it, would that be the same? Would that substitute for people that walk around, that go inside, that go outside, that go to the gym, that do this?
It wouldn't substitute for all of it. No question.
So to me, it's a very low level of exercise. If you didn't see anything from it, then
you wouldn't rule it out.
You wouldn't rule it out, right?
Good. So there are testable molecular hypotheses that link the biology of aging to anti-aging drugs and to exercise, and teasing out how those are interrelated and which of your exercise regimes, say, increase irisin, increase GPLD1, and increase neurogenesis, right? That's a research agenda that could be very valuable. And then if you want to screen drugs in people to see which ones deserve expensive long-term testing. The ones that raise GPLD1, irisin, and some aspect of neurobiological function in addition to the good stuff they're doing for the muscles. That's an approach.
Right. I agree completely. And this gets back to what we were talking about before with the epigenetic changes is if you had a mechanistic connection, which is what Rich is drawing there,
yes,
not only this is correlated with this outcome, but here's why.
Yes.
We all feel a lot more confident that this is real, right? That it's important. And especially if that mechanistic connection is preserved in people.
Good.
Do any of you believe that GLP-1 agonists are geroprotective?
Oh, I'm super interested in that question.
Yeah, I think we need to find that out. They look good.
I think there's two parts, though. Yeah. Are they geroprotective from a caloric restriction effect, or are there caloric independent effects that could potentially be geroprotective? I'm
actually asking the second question. Okay. I'm taking the first as a given.
Okay. Well, that's a different question. Is chronic caloric restriction beneficial in normal weight people? But most people taking GLP-1 agonists aren't normal.
Yes. And I think it's impossible at this point, because the studies are all done in obese and patients with type 2 diabetes, that we can't disentangle them. So we will just say that for that patient population, the caloric restriction appears to be geroprotective. But yes, you're right. I'm technically asking the second question, which is in an individual who is metabolically healthy but overweight, where there's actually no evidence that weight loss per se is necessary, outside of maybe some edge cases in orthopedic stuff. Is there a geroprotective nature to this? And where it's most talked about is in dementia prevention right now. Mm-hmm. That's where it's at least most complicated to tease that out. So what do you guys think?
And it clearly has neurological effects. There's effects on addiction, right? So the dementia connection is not
It's crossing the blood-brain barrier.
Right.
Yeah. I mean, Rich, this is one for you to test.
Yeah, why hasn't the ITP tested this yet, Rich?
Is it because the oral ones are just not strong enough and we want to? Yeah. Can you break your protocol and do an ITP with an injection? Why?
Because it's enormously laborious to do weekly injections.
That sounds like an I need more money problem.
And also you need a separate control group. Because
that sounds like an I need more money problem.
Needs to get sham injections and yes, if you increase our budget dramatically, I think it's a worthwhile experiment. But what we're waiting for is oral drugs that work, that you don't have to do injections of drugs.
I mean, there is an oral semaglutide formulation that's taken daily.
It was submitted to us this year.
Okay.
The detailed protocol, however, is, again, technically very laborious. Each mouse has to be food deprived for 6 hours. Then the material is administered, and then they have to have a change in their water balance for the next 2 hours. It is technically not an injection, but it is not any less laborious. And in addition, you have to have your own separate control group that gets all of those different manipulations with a sham injection.
Could you do 3 instead of 5 next year and make that one of them? Reallocate some funding?
Well, I'm not in charge.
It's a heavy lift. Yeah.
But I'd vote against it. I would vote for waiting about a year until somebody comes up with a pill that you can just mix into mouse food or water and give it to the mice, and it'll work.
And these are going to be mice that are an incredible amount of stress from all the handling, the injections.
Oh, yeah, that's why the control group is necessary. But the companies are putting so much money into this. They understand why people don't like to inject themselves. I'm reasonably sure, I mean, I know nothing about it, but I'm reasonably sure that in a year or two, there'll be some agent that works when you put it in the food of a mouse or the pop it as a pill as a person. Those would be enormously important to test.
Do we know if tirzepatide, for instance, if we're given to people of normal body weight, do they also lose 15% of their body weight?
Good question.
I have not seen the data on that. I can tell you anecdotally, having seen patients, it's going to be dose dependent. So as you know, that drug is dosed from as low as 2.5 milligrams weekly to as much as 15 milligrams weekly. Usually people who don't need to lose much weight, someone who says, look, I just want to lose this last 10 pounds and I've done all the exercising and dieting I can do. They typically just lose that 10 pounds and they take a very low dose. Now, to your point, if they took the 15 milligrams, would they become sarcopenic?
Right.
I don't know.
But I think, this conversation points out again, how constraining lack of resources are. I mean, there are
it's
probably
infuriating. Like
15
we could sit here and come
20,
up with 50 amazing questions that we can't
I mean,
answer.
every time I hear Rich talk about this stuff, it just pisses me off because there's a bunch of stuff that should be tested, should have been tested by now, that hasn't been tested, not because it's not a good idea, but because there just isn't any resources to do it.
Well, I think what's really frustrating as well is that these are the types of experiments that would allow us to actually start to economically model the impact of these drugs outside of just kind of a disease state. For example, if drugs like these are indeed geroprotective and people can work 3 years longer or 5 years longer because they're healthier, think of the impact on that over at OMB, right? What does that mean to tax take? What does that mean to delaying Medicare? What does that mean to reduced healthcare spending at the time when it is most expensive? So, boy, there's a lot to do.
Last estimate I saw was $38 trillion a year for every year of healthspan.
Wow.
That was a McKinsey report.
That 38?
I'll send you the link.
Not 3.8?
Nope.
38. Well, 38. But that's analysis by Andrew Scott, who's a British economist.
Whew. That's bigger than I would have guessed. Wow. Can we just, because I'm in the mood to see you get spicy, can we just talk about senescence for a minute?
Senescent cells, he means, Rich. You know, the things that drive aging.
Oh, tell me more. What do you mean? You want me to talk about senescent cells? Okay, yes, I'll be glad to do that. It's a terrible historical accident. Leonard Hayflick way back found that human cells would only divide 50 times and stop. One of his colleagues, a guy named Vittorio Defendi, made a joke at lunch and said to him, "Hey, Len, maybe they're getting old." Ha, 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 ha. And Len did not understand it was a joke. He thought it was a serious scientific hypothesis. It's clearly nuts because we don't get old in a way that is modeled by having embryonic lung fibroblasts stop growing. But at the time, the hottest technique in modern medicine was you could grow cells in culture. That was really so cool. You could do stuff with them. So all the cell biologists who really wanted to use the coolest new toys wanted to have a way of studying aging without all these messy mice and rats and having to wait and stuff. They could do it in vitro because this was in vitro aging. This is in vitro senescence. And the field, to skip 30 or 40 years, the field went ahead with this metaphor without ever questioning it. It's now such an industry that the people who review these grants and papers and advise billionaires and advise startup companies, they all were trained in labs that just do senescence for a living, so they never stopped to question. One of the most famous and best scientists in this area is a woman named Judy Campisi, who
recently passed away.
Died last year. She and I were assistant professors together at Boston University, and she and I were going to send in a program project with a third person, Barbara Gilchrist. I was going to study immunity and aging. Barbara was going to study skin cells. We talked, Judy, you want to study cell senescence? So she read the literature. She came back to us and she said, "This has nothing to do with aging. I mean, it's good cell biology. It's good about cancer biology, but of course, it's nothing to do with aging." And we told Judy, of course, it has nothing to do with aging. We understand that, but the reviewers think it is aging. So if you can just keep a straight face for the 3 hours of the site visit, pretend you think it has to do with aging, you'll get a great score. And that's what happened. She got a great score. We got the program project. When she moved to Berkeley, she took her grant with her. And after a year or two, she had apparently convinced herself that it was aging. It was close enough to aging. So the notion that aging is due to senescent cell accumulation is bad for two reasons. It's a grotesque oversimplification. The evidence for this is awful. But even worse, it again cuts off productive thinking. There almost certainly are changes that occur in some glial cells in the brain so that as you get older, they start making bad cytokines that's bad for your brain. There probably are changes in some bone marrow cells or some cells in the lineage that leads to the beta cells in the pancreas that lose the ability to divide. And that's bad for you. And finding out how it happens is really important. But once you've convinced yourself that's all the same thing, this cytokine, this also proliferation, this change in ability to make specific fibrous connective tissue, let's call that senescence. It's the same thing. You've lost what you need to think of good, careful, well-defined experiments with well-defined endpoints. If you say that there is a thing called a senescent cell, the thing that's happening in this glia and in this marrow cell and this pancreas, it's due to the senescent cell accumulating. You've blocked off productive generation of research hypotheses. The last point I'll mention in this rant has to do with senolytic drugs. So the ITP was asked to test an allegedly senolytic drug called fisetin. It was given to us by someone who is using this now for clinical trials and who has a company that's interested in senolytic drugs. So we gave it to mice. It had no beneficial effect whatsoever. At the dose,
what's the mechanism of this drug's action?
Oh, it has no action. Okay. I mean,
has no action, or
well,
it had no
have
effect?
It had no effect.
Okay.
What is it supposed to do? It's supposed to kill senescent cells or something.
Okay.
So we told this guy, sorry, it had no effect. He said, well, let's prove it, whether it had any change in senescent cells. So we gave him blind tissues from each of the treated and untreated mice, and he tried a test, and there were no changes in senescent cells by his marker. He tried 6 different markers. There were no changes in senescent cells. So then he said, well, send the brain and the liver and the muscle. Maybe the senescent cells have been changed in the brain. So we sent blind samples to a colleague of his. There were no changes in senescent cells by any of the markers that these folks looked at. So this drug, which is now being marketed in clinical trials, and you can buy it, I'm sure, as an
it's a natural product. Yeah.
It's a supplement.
Yeah. There's no evidence, as far as I know, that it either has an anti-aging effect or removes senescent cells. But once you've got a commercial company pushing this stuff, and your whole brand, your whole lab, your whole program project, and all the people who are reviewing you are convinced senescent cells exist, they're bad, and drugs can kill them, it's a snowball rolling downhill, and a rant of the sort I've just delivered has no impact on the field.
So can I give a counter example? Because there's good experimental data that these things can be at least partially eliminated, and when you do that, there's an improvement in health. And this has been done both in a genetic treatment, which they prime these cells to be genetically killed, and it's also been done with drugs, not with fisetin, I hasten to say. So I think there's strong evidence that getting rid of these P16 positive cells, which is really what it's all based on, can have an improvement in health and in longevity.
Is the Van Dersen paper you're talking about in which they were allegedly depleted?
Yeah.
Let me tell you about that, because I was on the program project. My job in that program...
2 papers. Okay, one was with the short-lived mice, and
yes.
one was... Okay, so
I'm
tell
going
me.
to talk about the one that is not the short-lived mice. There's a famous paper by Van Dersen, Kirkland, and several other colleagues, Darren Baker.
Are these the guys at Mayo?
Yes.
Yeah,
They
okay,
were,
I remember
yes.
this. Yep.
They've left. 2 of them have left. But yes, they alleged that they could remove senescent cells by taking genetically modified mice, giving them a drug. All the senescent cells would go away, and the mice lived longer, according to the paper.
This was on the cover of Nature.
It was on the cover of Nature.
I remember this one.
I was a part of the program project. So was Judy Campisi. And my job was to do the lifespan experiment. We got the mice from Kirkland and Van Dersen. We got Campisi's mice. We got the drugs from them. And we gave the drugs to the mice at 18 months. And, they had no effect on senescent cells. Not one. We tried 7 times to show depletion of senescent cells in their mice using their drug, and went 0 for 7. We then took the tissues, blinded, and sent them to Judy Campisi's lab, so she could measure P16 cells. But she didn't know which ones were from treated and which ones were untreated. When we undid the code, there was no effect on senescent cells whatsoever. So I remained somewhat skeptical. I asked Van Dersen, Had he measured the number of senescent cells in his treated mice? No, we're planning to do that.
But what was the phenotypic change in the mice when you did this experiment?
When I didn't want to do an expensive lifespan experiment with an alleged anti-senolytic drug until I knew that it was depleting senescent cells.
So how long did you treat for?
I used their protocol, and I asked Darren Baker, what is the dose? How long do you treat the mice? And how long after you add the drug should you wait before you detect the removal of senescent cells? And his answer, astonishingly, was, we don't know. We've never looked at that.
But the nature mice were treated for how long?
They were a long time.
Their whole life.
A long time.
They were treated. I think they started treatment in middle age, right?
And I mean, in the published papers, they do show a reduction in P16 positive cells. And you're saying you couldn't replicate that in your lab. Is that?
But we're conflating a bunch of different issues here. We're conflating the genetic model with the drugs. And do senescent cells even exist? And I feel like, I think Rich's skepticism is valid in many ways. And there's actually a large body of evidence that whether we agree on the definition of senescence, what people are calling senescent cells do accumulate in multiple tissues with age in mice and people. And if you get rid of them, you can see some health benefits. Am I convinced they have big effects on lifespan? No, I'm not, because the data is mixed. And even that genetic model, other people haven't been able to reproduce. So it's messy. But I think partly maybe start with what is the definition of a senescent cell, because that's where a lot of this confusion comes from, right?
That's what I was saying, that there is no satisfactory definition. There are many things that...
Satisfactory to you. I mean...
So is your issue, Rich, that we talk about it like it's one cell, but in reality...
Big part of it. You can't think about it clearly if you imagine that these many, many different kinds of cell intrinsic changes with potential pathological impacts are all aspects of the same phenomenon.
But we do that with other things. We do mitochondrial dysfunction. There's lots of different ways to get to mitochondrial dysfunction.
So the NIH has just put about $600 million into a network of researchers to study cell senescence. And I'm on the advisory group for that. And to the extent that Rich is saying these are many, many different things, all pretending to be the same thing, that's clearly true. But they're coming up with bigger and bigger and broader definitions of what a senescent cell is. But on the other hand, they're also coming up with more and more interesting things that those senescent cells do in tissue culture, which I don't put much, or in mice. So, I don't think the NIH would put that kind of money into something if they didn't feel there was a valid basis. I think part of this is we're calling it senescence. And I think none of us, to me, that's stolen a really good word out of the vocabulary, because senescence just means aging. And it used to be, you could talk about calendar aging, you could talk about senescence, which is what we now think of as aging. And now you can't use this anymore because anytime you do, they think you're talking about these cells that...
It's an easy analogy.
Is this what they call the zombie cell? I keep forgetting.
That's an analogy.
I keep trying to purge that from my memory.
So, the most common definition, I think, is just an irreversibly arrested cell that doesn't die and typically gives off a pattern of inflammatory cytokines and other factors, and which is a catch-all for a lot of different ways to get there and a lot of different states that these irreversibly arrested cells can exist in.
Yeah, but even neurons, they're not considering senescent neurons, and neurons are, they're post-mitotic.
Right, but they don't always give off this pattern of signals, right?
That's
again,
right.
This is part of the problem, is you mentioned P16. I think even at the molecular level, the catalog of markers that people are using to define a senescent cell is changing, and it seems to change.
Broadening, yeah.
So I agree. I agree with much of what you're saying. I just don't think we should throw the baby out with the bathwater here and say there's nothing to this. I think there is something to it, and I think there's lots of evidence that are there enough similarities between all the different classes of senescent cells that people are studying now that they should be categorized as one thing? I think that's a valid conversation to have. It's a good discussion point. I don't think we know the answer yet.
And they discuss this a lot in the Senect, because even the SASP, even these things that are oozing out of the cells, varies quite a bit depending on the nature of the cell.
That's the problem, of course. You referred to it. as almost anyone would, as the SASP, the set of senescence-associated proteins, secretory proteins. And once you think of it as the SASP, you've lost. Because the key point is not to do that. The key point is, here's a set of cytokines that this cell has begun to make. That's really interesting. Here's another set, overlapping probably. They make it when you've made them stop dividing for a separate reason. That's interesting. We should study that. But to think you've proven something about this cell type when you've actually been looking at this cell type because the SASP has been changed.
But do you think it's possible that a drug such as rapamycin has part of its effect on aging through a broad inhibition of a subset of the SASPs?
By a bizarre coincidence, we have, I think it's very likely that rapamycin changes cytokine production by many different cell types, and that some of those changes would probably have health benefits. I would like to know what it does to the cytokine production from the macrophages in the fat and the glial cells in the brain and cells that are in charge of protecting you from viral infections. But the mistake is to say, yes, it's affecting the SASP. It's easy to see an analogy. If I said, here's a drug and it helps you because it affects neurons, you'd laugh at me because what you really want to know is it motor neurons, sympathetic neurons, parasympathetic neurons, neurons in your hypothalamus, what part of the hypothalamus, the ones that control appetite. And I said, no, it affects neurons. I've got a drug that affects neurons.
But I mean, people are aware of these complications and are studying these complications now. It seems to me that it's the terminology that you object to, and I can appreciate
it's thinking that I object to. The terminology is problematic because it makes people stop thinking about the important details and start imagining that they've had a thought when they say, I have a drug that removes senescent cells. The problem is that the words trap you into patterns of thought that are, in this case, non-productive and misleading.
Maybe inefficient, but the field is making, I would say, quite a bit of progress. And I think the way you learn about the complexity is you start with a simple model, you study it, and then your model gets more complicated. So I totally get the frustration, Rich, because I get as frustrated as you are about senescent cells, about other things. But I think this is also part of the natural process here. And I think what Steve said is really important. The fraction of the NIH budget that goes to study the biology of aging through NIA has remained tiny. But senescent cells are actually a really good example of how a bunch of people in other institutes are studying aging and they don't even know it. They're studying senescence in cancer, or senescence in Alzheimer's, or senescence in kidney disease. So it actually has had an impact in kind of broadening the appeal and scope of the field outside of NIA in ways that I certainly didn't anticipate.
Do you think that, going back to the meta problem at the beginning of our discussion, do you think that's maybe a better way to think about allocating funds? So, for example, the NCI obviously receives the most funding within NIH. Maybe some of the NCI funding goes to the NCI to study cancer prevention through geroprotection, right? If the turf war is what matters.
That's a good idea.
I'm all for it.
No.
Yeah.
We've actually, a group of us who are lobbying the Congress have actually asked the NIH to tell us exactly this. How much work in geroscience is going on in all these other institutes? Yeah. Of course, they're going to have some motivation to minimize that or maximize it or something, but at least it will give us an idea. Right now, we have no idea how much of the NCI budget is going to this or NIDDK or anything else. So they already have produced a report that told us how much they were spending in the NIA, but we already knew that. We wanted to know how much they're spending in the other institutes.
I mean, I think that could alleviate some of the turf war issues, but I think what you really need is, the change in leadership and leaders who actually recognize why this is important. And that's where it starts. I mean, we can have a conversation about how much power does the NIH director have, how much power does the director of HHS have, but that's a place to start. If you can get people in those positions who get it, it's going to have an impact.
Let's talk a little bit about metformin. Rich, do you think metformin is geroprotective in humans? I know it doesn't appear to be in your mice.
I think the evidence is uncertain. There's a famous paper from Bannister that alleged that diabetics on metformin had lower mortality risks than age.
You don't listen to my podcast, do you?
I do occasionally when
actually no. You know what? It was a different podcast. I did a very lengthy treatise in a journal club comparing the Bannister paper to the Keyes paper.
Good.
And came to the conclusion that the Bannister paper had too many methodologic flaws to be valid.
That's exactly what I was going to say. And as a matter of fact, Keyes, Christensen, who's the senior member of the group, and I have just written a review article which says exactly that. That's the title of our paper. Is it out yet? It's under review. So yes, so you know exactly what I was going to say, and I agree completely. The question as to whether metformin would be geroprotective, that is
in a non-diabetic,
non-diabetic in humans, I think is interesting, unanswered. It's not the drug I would have looked at myself if I had a big set of dogs, for instance, and I wanted to give them a drug that modified their glucose homeostasis. I would probably start with something like Canagliflozin that actually does work in mice and which is known to be safe over the long term in people. Metformin is safe over the long term in people, but I don't think there's much evidence that it's anti-aging, leaving aside how great it is for diabetics and pre-diabetics.
What do you think, Steve?
I think it's very promising. You know, I'm skeptical because I'm always skeptical in the absence of evidence, but the observational evidence, ignoring the Bannister paper, just the consistency of the observational data that it reduces dementia, cancer, cardiovascular disease, suggests to me there's enough smoke there to look to see if there's fire.
I'll send you the Keyes review article, and then you can rethink that.
Okay.
But sorry, Steve, you're saying it does all of those things in diabetic.
Well, most of the studies have been done in diabetics, absolutely. Yeah. And how much of that is just because you're curing the diabetes is an open question, but I think it's...
And how much of that is a selection for people in diabetes that are progressing much less slowly because they're the ones that stay on a single agent as opposed to the ones that progress into...
Right, but which is why you have to do the study.
Yeah.
You know, the question
where is TAME in the world of...
TAME is in a very preliminary state. There's now enough money to get it started. Previously...
So it has not enrolled anything
It's
yet?
enrolling right now.
Okay.
Previously, they didn't want to start it until they had enough money to do the whole thing, but it's been impossible to get that. There's now a small amount of money, enough to get it started at a small scale with the hope that that will sort of start the pot rolling. But it's been around for 8 years now. And I was in on the original discussion about, do we do rapamycin, do we do metformin? And it was all about cost and safety. That was the whole thing. I went in strongly advocating for rapamycin. I came out saying, okay, there are these cost issues. And I think it was important because when we went to the FDA, we didn't want them to think that we were trying to make a bunch of money with this trial. And nobody's going to get rich from metformin.
Why is generic sirolimus so expensive still?
I think it's supply and demand, honestly. I think
they just haven't, there's no need for them to ramp up production.
Yeah, I think so. Yeah. But coming back to the metformin question, I mean, I think, first of all, we don't know the answer. I mean, Rich is right. We don't know. So what are our opinions? My opinion is diabetes probably accelerates biological aging, and metformin is effective at reducing diabetic symptoms and probably reduces biological aging in that context, probably doesn't in people who are not diabetic. That's my intuition.
And let me push back on that for a second, sure. Which is diabetes is an artificial diagnosis in that we just make a cutoff. We say your hemoglobin A1C is 6.5, you have type 2 diabetes. Sure. If your hemoglobin A1C is 5.9, you don't. But there are data that we've looked at that suggest a monotonic improvement in all-cause mortality as average blood glucose goes down, measured by hemoglobin A1C, in the non-diabetic range, meaning people with an A1C of 5 live longer than people with an A1C of 5.5, live longer than people with an A1C of 6, all of whom are non-diabetic. Point being, if metformin's geroprotection comes through the regulation of glucose in the patient with diabetes, does it stand to reason that even in patients without diabetes, further attenuation of hepatic glucose output is going to improve all-cause mortality?
Maybe. I don't know. I don't know the answer, obviously. I think the question is the biomarker, in this case, A1C, what is that actually reflecting, right? Is that presumably reflecting some aspect of metabolic homeostasis, right? And so, first of all, does metformin in non-diabetics have the desired effect or the effect we would associate with reduced mortality in non-diabetics consistently? Be question number one. I don't know the answer to that. You probably do.
And I don't want to speak for Nir because it's been a while since we've spoken, but the last time I had Nir on the podcast, his rationale for why metformin was geroprotective had nothing to do with glucose homeostasis in a non-diabetic. It was, and I know you're going to love this. I mean, Rich, you're really going to love this. There was a figure of the hallmarks of aging and how metformin acted on each of them.
Sure. Which is, I mean.
But my point being, not to say that that's incorrect, correct, or anything. It's that there was something much more primal about metformin's actions. Now, here's my pushback on that.
Primal.
Metformin requires an organic cation transporter to get into cells, as I've learned somewhat recently, that muscles don't have. So if you look at the tracer studies, metformin does not get into muscles. It gets into enterocytes and the liver. It's very concentrated in the liver, gets in the gut. Unclear from these tracer studies if it's getting into immune cells. So Nav Chandel tells me that he believes they are getting into immune cells as well. So the question is, at least I think we need to ask ourselves the question, if it's working, which cells is it working on and how? And so the liver part's easy. Everybody gets big concentration of metformin shows up here. We sort of understand that reduces hepatic glucose output. After that, I'm sort of scratching my head going, I don't know how it works.
Well, we know it has a target in the mitochondria, complex 1. It inhibits. We know
but
it affects.
Which cells? Besides that's my point. Like it's not in the muscle.
That's a question. Yeah. And we also know that it activates AMPK.
Yep.
Interestingly, a friend of all of ours.
Those mechanisms are probably related.
Yes. Yeah, and that could explain.
This is why Nir points at 2 of the hallmarks. I just have to tell you this. But here's an interesting thing. A good friend of ours, George Martin, who died a couple of years ago, once went through and cataloged all the human diseases he could and tried to look at the similarities of their phenotypic changes relative to what happens with normal aging. He came up with diabetes as having the most similarities to accelerated aging of any of the groups that he looked at, which
and it makes this sense. The glycosylation, the hyper growth factors like insulin, IGF-1, all these things. I mean, there's logic to that.
Well, let me agree with the emphasis you were just putting on organ-specific and tissue-specific changes. And I think it's about time to get away from what does metformin do to the body, or any of these drugs for that matter, and start to think what does it do to each of the interesting players and how they talk to one another. Someone in my lab has been looking at the enzymes related to de novo lipogenesis, and she's been looking at a couple of different kinds of slow aging mice, and it has major effects in the liver, and it has major effects on the white and brown adipose tissue, and they go in different directions. And which is primary, which is reactive, whether any of these are related to the effects of the mutations on the muscle or the brain is now an open question. So having a diagram of hallmarks which are changed by a drug is much less useful than asking what specific changes in what cell types of which organs that talk to each other are being changed by this drug as a primary or as a secondary or as a compensatory effect. That's how you'll start to get into first mechanisms, but also start to be able to think clearly about ways of targeting therapy so that it has a benefit with fewer and fewer side effects.
So let's use canagliflozin as an example.
Yeah.
We've demonstrated, and I use we very liberally here.
Yeah.
You've demonstrated that it reduces all-cause mortality in your mice.
In males.
In males. Do you believe, and we know exactly what canagliflozin does in the kidney, and we know that those mice live longer. Do you believe that the longevity benefit came through glycemic control? Because there was no difference in weight, if I recall.
They actually lost weight. Males and females lost weight on canagliflozin. But the question is...
But was there a difference in weight between... So what was the difference in weight statistically significant between the long-lived males and the normal males?
The mice treated with the drug were lighter in weight than controls, and that's true of both sexes.
So the weight loss wasn't necessarily what explained.
They actually lost more weight in females than in males. So the question is very valid, and we do not know the answer. SGLT2 is on many other cell types. And it's quite possible, very plausible, that canagliflozin had an effect principally through controlling peak daily blood glucose, not average, but peak. And it's also possible that it had effects on cells of unknown origin in the brain. And all of these are very valid, and I don't think anyone knows the answer. It's well worth evaluating. There are other inhibitors of SGLT2 and SGLT1 that have differential cell specificities and differential effects on different cell types. And looking at those would help give you glimpses into this question. We guessed it had to do with glucose, but we might be wrong.
So what is your intuition, Steve?
Well,
Going back to metformin.
My intuition is that it might work. I don't have a strong opinion. There's enough suggestive evidence that I think it's worth a trial. And I think that if we wait until we figure out exactly what each drug does in each cell type, it will take us forever to get any therapies. And in medicine, there have been many, many advances that came about before we understood the mechanistic underpinning. And if there's enough suggestive evidence and there's not a lot of side effects, suggests me that it's worth digging into now, because the benefits are so enormous. Like we said, 1 year healthy aging, $38 trillion. That's, that makes, that should talk to Congress if nothing else does.
Yeah. Well, and I would also say TAME could be successful independent of whether metformin is effective at slowing biological aging, right? So those are not necessarily...
By getting others into the field, you mean?
Well, also even just hitting the endpoints, right? So the endpoint is multimorbidity, right? Or comorbidity.
Right.
So it's quite possible that the trial will be successful, even if metformin is not a effective gerotherapeutic.
Yeah.
And the opposite is also true, right? It may not succeed for a variety of reasons that clinical trials don't succeed. I sort of agree with Steve. Like I'm supportive of doing the trial. I also agree, I think, with probably both Steve and Rich, that it's not what I would pick if I was going to do one trial, if we could only do one trial, but we have to start somewhere.
Matt, why do you think that the ITP studies for rapamycin always worked, regardless of which start young, start old, give it with metformin, do it by itself? It always worked, and the mice are taking rapamycin every day?
Because inhibiting mTOR increases lifespan and slows aging. I know what you're asking.
Yeah,
you're asking,
you know where I'm going.
Because most people who are using rapamycin off-label have moved to once weekly or some sort of cycling like that. And so I think one question is, would that increase lifespan in mice as much or more than daily? We don't effectively know the answer to that question, I don't think.
Didn't you guys do some intermittent?
It can increase lifespan, but it's never been dose optimized, right? I think this is the question, right?
Is the metabolic rate of the mouse so fast that giving the mouse daily rapa is not the same as giving the human daily rapa?
Yes, and the rapa in the ITP study is in the food, so it's not even a single dose, or it's not a single.
They're just
dose.
chowing on it all day.
Well, at least during the period of day that they're eating and have access to. I mean, I'll let Rich talk about what they know about the blood levels, but it is a fundamentally way of delivering the drug.
Why did you guys decide? I mean, I guess in 2008 when you did the first study, maybe it wasn't clear, this idea of mTOR1 versus mTOR2 and the constitutive dosing.
Maybe we should ask how many people at this table actually believe that model.
Yeah, that's kind of where I want to go, right? I want to understand what we think is true and not true about rapamycin based on this experience.
I guess I don't understand the question. Do we believe what model? What are you asking?
That the bad side effects come from mTORC2, off-target effects of rapamycin, and all the good stuff comes from inhibiting mTORC1.
I don't know enough to say. Many of our slow-aging mice actually mTOR complex 1 function is down in all of them, but mTOR complex 2 is often up. And it's up in an interesting way. Mice eat mostly at night, and they more or less fast during the day. In our slow-aging mice, mTOR complex 2 is elevated, but it no longer responds in the fasting period, but it doesn't respond to food in the same way. So their complex changes in both its baseline state and its response to food. Whether these would happen in people taking it every other day, every fifth day, whether they are beneficial or harmful or a mixture, I really don't know. The mTOR complex 2 story is trickier. The other thing that is, I think, important but not really appreciated is that it not only mTOR complex 1 drugs like rapamycin not only lower the overall effect, but it also changes the substrate specificity so that the kinase that is susceptible to TORC inhibition that looks at a ribosomal protein, S6, that goes down. It doesn't work nearly as well. It's inhibited. But the kinase that...
For how long?
I don't know. But the other aspect of TOR downstream is on a protein called 4-EBP1 that's involved in translation. It does not change that kinase. What it does is it changes the total amount of the protein. So the proportion of the protein that's phosphorylated drops down, but the actual kinase that adds the phosphate to that substrate is unchanged. So whether that's important, that it's having at least two different pathways that are being influenced in one case by changing the substrate and in the other case by changing the kinase, no one's really looked at that. They say it's a drug that blocks mTOR kinase 1 function. And downstream is where a lot of the action is. I know your lab at one point was interested in cell type specific inhibitors of the TOR complex 1. I don't know whether
everything you just said, Rich, occurs in what cell?
Liver, mouse liver.
What about muscle?
Well, the overall decline in the ratio of phosphorylated versus substrate was we also published that, I think, in Muscle and Kidney. I would have to go back to the papers and see whether we also found the elevation of the substrate, the 4-EBP1, in both of those tissues. I vaguely recall that it was the substrate that changed, not the kinase in those tissues as well, but I'd rather look it up before I sort of sign my name to it.
But even what Rich is saying is while, I mean, really important and informative, also really only a tiny piece of all the downstream things that mTOR affects. And I think the point is we just really don't have a good understanding of how rapamycin or fasting or other drugs that hit mTOR are affecting all of the things that are downstream of mTOR.
I agree completely. Let me give you an example. So Linda Partridge just published in BioArchive, at least, a nice paper. Rapamycin increased lifespan for mice. If she added an inhibitor of a different kinase called ERK, it did better. It did. The inhibition by ERK worked by itself, but it actually improved on rapamycin. So two people in my lab are looking at that, and it turns out that the ERK kinase inhibitor is working in an entirely different pathway. It's affecting the proteome by increasing the degradation through a chaperone-mediated autophagy mechanism, which is not affected by rapamycin. So
at least at the dose they used, right?
At least at the dose they used. Right, that's right.
Sorry, what model was this? This was mice?
Mice.
Mouse liver,
Probably Black 6.
No, we never used Black 6.
No, not you. I'm talking about the Partridge paper.
No, it was an F1 hybrid.
Oh, okay.
Actually. So it's agreeing with and amplifying the question, there may well be multiple cell intrinsic pathways, some of which are TOR dependent, some of which are MAP kinase, ERK dependent, which can synergize, as in the Partridge case, for lifespan, but also potentially synergize for health impacts.
Yeah, and here's I mean, I think an important, again, limitation to what's been done. There are drugs out there that hit both types of kinases, right? There are drugs out there that are ATP competitive inhibitors that have different affinities for different types of kinases. Haven't been tested for longevity. These dual kinase inhibitors, right? In fact, in the Restore Bio trial, the last one, the phase 3, which did not get to completion, they substituted. They took the Rapalog out and used an ATP competitive drug.
I didn't know that.
So what is your belief, Matt, around dosing Rapa in humans then, or even in your dogs.
Yeah.
You're doing it in...
We're doing it once a week now. We've moved to once a week. So, I mean, maybe it's worth at least talking about how that evolved. And this is my understanding of sort of how we got to where we are today, which is that most people using rapamycin off-label for potential health span effects, most doctors prescribing it are recommending once weekly dosing, in the 3 to 6, sometimes 8, 10 milligram range. So the first place I'm aware of in the literature where this was shown to have a potential benefit for anything related to aging was Joan Manick's work when she was first at Novartis and then at Restore Bio looking at flu vaccine response in elderly people. And they were using everolimus, so a derivative of rapamycin. And they found that for vaccine response, it was most effective and had the least side effects at once weekly dosing at 5 milligrams. Yeah, and they tested daily 1 or 2 mgs, 5 mgs once a week, 20 mgs once a week.
Yeah, it was It was a milligram a day, 5 once a week, 20 once a week. Now I've had both Lloyd Klickstein and Joan Manick on the podcast. It's been so long that I don't recall if I asked them why they designed the trial with those 4 arms.
So my understanding is that Novartis had internal data at that point on side effects and had an internal hypothesis that if you let the trough levels bottom out, that reduced side effects. So that the side effects in organ transplant patients were largely driven by high troughs. Yep. And then after that, they developed based off of David Sabatini's work and then Dudley Lamming after he left David's lab, a hypothesis that chronic treatment with rapamycin, which maybe would be equivalent to daily dosing in people, this was all done in cells, led to off-target effects on mTOR complex 2, and it was mTOR complex 2 effects that were driving the side effects. So that got sort of dogmatized as the truth, and I actually don't think there's a ton of evidence beyond those initial papers to support the idea that the side effects are all through mTOR complex 2. But the idea is if you dose once a week, you could let the trough levels bottom out. You don't get the off-target effects on mTOR complex 2. You avoid the side effects. Again, we don't have definitive data. The data I've seen seem consistent with that idea. People dosing daily seem to be more likely to have side effects, mostly things like bacterial infections or the really severe mouth sores, but it's sort of anecdotal, and I don't know for sure how strong that data is in people. It did hold up in all of the Restore Bio clinical trials that I'm aware of, that once weekly dosing really didn't show any side effects different from placebo.
In the dog study, you're using a slow release formulation. Is that correct?
It's an enteric coated kind of. It's a different formulation than what the ITP uses, but all of the human sirolimus formulations have some way to get to the small intestine, right? So it's not substantially different, I don't think, than Rapamune or the generic sirolimus that you would.
Let's do the closest thing that a group like this could do in terms of a speed round. I'm going to go through a couple of other ideas. I just want to get what are you thinking about this? Can we say anything positive about resveratrol?
No.
Rich?
No.
Why does this thing not die? Why is there still 100 different resveratrols being sold on Amazon? Why do I still get people asking me, do you take resveratrol? Should I be taking resveratrol?
It has a good PR team.
I think it's really hard to prove something doesn't work, right? So once it gets in the consciousness as improving health, even in the longevity field, Jesus Christ, I was saying the resveratrol stuff was garbage for 10 years before people believed it, right? Now everybody believes it, but it takes a really long time. Well, right. At least in the aging field, I think if you went, you never see people studying resveratrol in the aging field anymore. I think if you went to a conference and asked scientists, what do you think about resveratrol? You'd get the same answer here with maybe one exception. But I think it takes a really hard...
Just one exception.
It takes a long time to
Bad ideas don't die hard.
That's right. And that's true in the scientific literature. And it's especially true when there's a profit motive to continue selling this stuff. And Like, I'm not 100% convinced that there are no health benefits from resveratrol. I'm pretty convinced there's no reason to believe it affects the biology of aging or is a longevity drug, but I can't say for sure that nobody would ever benefit from any dose of resveratrol.
Yeah, but we couldn't say that about anything.
I agree.
Right? Yeah. Now, we could say that if you were force-fed the highest fat diet in the world, such that your liver encroached on your lungs through your diaphragm, isn't there a chance, Rich, that under that situation, resveratrol might help?
I have no idea.
Wasn't that the one and only one experiment that worked?
Yeah, the famous experiment, which was published as resveratrol, the first drug ever found to extend mouse lifespan. It turns out that the mice die because they were on a 60% coconut oil diet, and it's poisonous to the extent that it causes the liver to fill with fat and compresses the thorax so that they cannot inhale. 3 or 4 papers later, they published as an obscure paragraph in a discussion section on a paper. Pearson was the first author of the second paper that, oh, by the way, all these mice on the coconut oil diet, finally, we've looked at them. They're all dying because of lung compaction due to expansion of the liver. So the notion that their drug had slowed aging because on the 60% coconut oil diet, it temporarily extended lifespan was due to the prevention of this extremely bizarre phenomenon.
I just cannot get enough of that story. And
it's all documented in the literature.
I believe I know it well.
I mean, 2 separate papers.
All right, let's have a word on NAD, NR, NMN. Steve, what is your point of view on this?
Well, the current state of evidence, I'm skeptical. It's one of those things that makes a great deal of conceptual sense, but the evidence at this point is not very compelling. And we have the ITP evidence that is, I think, the strongest. And there was
strongest negative evidence.
Yes,
yeah.
Yes,
okay.
Yeah.
Just to make it clear.
I assumed that people knew that. I guess I should.
Okay.
So,
and is it your view, Steve, that, well, this stuff probably does not extend lifespan, but maybe there is some other health span benefit out there that has just not been studied. The right experiment hasn't been done. It hasn't been powered correct. Pick your favorite excuse.
I think NAD is a very, very interesting molecule, and I don't think we could throw out, manipulating NAD as something that could be important for aging. I just don't think the evidence is there at this point.
Do you think if you're going to manipulate it, you would have to do it with really, really high intravenous doses, or do you think you could achieve those levels using oral precursors?
That I don't know. I will express complete ignorance on that.
Matt, what is your point of view on all of this?
Yeah, well, I think the way you framed that question to Steve is indicative of why it's so hard to disprove something, especially when there are people out there who have money to make who really want to make the case that you should buy this stuff, because it's always possible that there's some way that this could be beneficial. Having said that, NAD, like Steve said, central molecule in thousands of chemical reactions, really important. Good reason, I don't know about good reason, some reason to believe that NAD homeostasis declines with age, like lots of many other things. So it's plausible that if you fix that, you can get benefits from it. The data is decidedly mixed, both in the literature, preclinical literature, and in people as to whether or not boosting NAD increases lifespan, improves health span. So I think there's lots of issues here.
What's the most positive data you would point to?
Well, for lifespan, the original study by Johan Auwerx's lab, where they started treating, I think at 20 months of age, was published in Science, I believe, showed an effect that was reasonably good sized, except the controls were short-lived, which is a different issue. Yeah, it's a different issue, right? You see a lot of, there are a number of cases where something was reported to increase lifespan when the controls were short-lived, and then when the study was repeated in longer-lived controls, you didn't see an effect. So I don't know why there was a difference between that study and the ITP, but that's probably the best case you can point to. There's studies in C. elegans as well that where NAD precursors increase lifespan. So there's evidence out there, and again, it's plausible. The biology is plausible. But then I think when you talk about the precursors, it's even more complicated than maybe boosting NAD could slow aging, because can you get the right doses in people. You talked about bioavailability. Is there any difference between NMN, NR, niacin, nicotinamide when you take it orally? The data suggests that it all gets broken down to niacin in the gut. So why are people taking, $70
super expensive
NMN
things when
or
they
NR?
can...
Yeah, why are people selling it? The people who are selling it, who some of them are scientists, dodge that question. I mean, it's complicated. I don't personally believe there is enough evidence to think that NAD precursors, as they are being marketed today, are likely to benefit most people. Some people, probably people who have conditions of dysregulated NAD, could get a benefit. I don't think there's any difference between the various molecules that are being marketed right now. And there's at least one study in mice that giving NMN to aged mice causes kidney inflammation and potentially kidney pathology. So there's, I'm not saying NMN's dangerous, but when you try to weigh the risk reward, if it causes kidney pathology in aged mice, at least at high doses, could it do the same thing in dogs or people? Yeah, it could. And it bothers me, particularly in the companion animal space, that people are marketing NMN for people's pets when they know that it might cause kidney disease in people's dogs and cats. That's problematic to me.
We talked briefly about parabiosis and plasmapheresis. Let's come back to it a little bit. So, Steve, is there going to be a day when the substance found in the blood of someone much younger than you, when infused into you, whilst some of your old blood is removed, is going to, assuming we figure out at what frequency that has to be done, impact your life?
Yeah, I think this is an incredibly interesting question, and it really deserves to be investigated in detail. Because if it's true, it's a real game changer, because we do transfusions. I mean, this is not exotic medicine. I think we very much need to know whether this works the same way in people. And also it would be nice to know how much of it is due to the
taking out
young
versus
blood
the putting in.
How much of it is getting rid of the old blood. But the evidence from mice is very, very compelling, I think.
Steve, if we could design the perfect experiments that would try to ask these questions, and let's just say we started by doing just the one experiment, which was the full parabiosis, so the putting in, the taking out, we didn't try to disentangle the effect, and there was no benefit in humans.
Mm-hmm.
What would be your best hypothesis as to why it would have failed, assuming it was statistically powered correctly and there was no methodologic error? If this was a biologic result, why would you think, given how favorable this has been in mice, it would not occur in humans?
That the products that ended up in the circulation of humans was a very different nature than in mice. I mean, the number of things that differ between humans and mice in blood would be enormous. So pinning it down would be. But I think there probably is some reason to suspect that it may work. I mean, I'm very impressed.
If it does work, this is an opportunity that, this is not like we had the technology to do this 50 years ago, right?
Right. And it may not work in young people, right? But it may work in older people. I think there's a lot of drugs that could affect aging that, because young people haven't aged as much, might not have minimal effect. But you give it to somebody that 50 years later might have a big effect.
I think I find myself frustrated by the question rather than by the answer, because
you got a horrible question asker here, Rich, is the problem.
I think you are well above average, but this particular one I think is illustrative, because the reason people like parabiosis is that they've seen it in a sci-fi movie. It sounds exactly like what you do in sci-fi, and they're flashing lights, and it's so sexy, and it's just so great, and you can take the blood of young virgins and give it to old people, and they stand up and they can get on the
I didn't
rowing,
realize they had to be virgins,
by the way.
Okay.
So, but none of that is pertinent. Pertinent is there something that is in the blood of old people that it would be good to remove? And if so, what is it? And is there something, a cell, a molecule, a set of 3 molecules that's in the blood of young people or mice that would be good for you? The only virtue of this parabiosis circus is to suggest that, the answer might be yes. There might be something you could remove from old blood, a cell or some plasma molecule, and there might be something good in the blood of young individuals. So the challenge now is to find out what those things are, and then you can do real-life science. Real-life science is not done by taking blood from young people and putting it into old people. That's medieval science, where is a complex mixture of dozens to hundreds of potentially...
Right, but that could be the proof of principle, right? In other words, you might start with that, and no one thinks that if you do that experiment where you literally take blood out of an old person and discard it and take blood out of a young person and, put it in, and you get a favorable result, nobody thinks that that's what's going to the FDA. That is the proof of concept that says what was it.
What experiments? You have a limited amount of volunteers, doctors, and money. What experiments are most informative? And in my view, by far the most informative experiments are what is in the blood of young mice that is so good, and what is in the blood of old mice.
But I don't know, would you want to go on that fishing expedition until you at least saw a signal?
Yes.
People are doing it. I mean, there are companies doing it.
Of course they are. I'm asking a different question, though, which is...
Yes, that's the only way you can turn your idea into science.
Well, I don't know. On the other hand, if it has a positive effect, I don't think it really matters. That's something to be investigated later. My thought is it's not simple. It's not one thing. It's not GDF11 for sure. If it were simple, there's enough people looking at it, they would have figured it out. My guess is some combination. If there's something there, there's some combination.
But why can't you do both? I think Peter and I are saying the same thing. Yeah. I think, would we love to understand the mechanism? Yeah, absolutely. Do we have to understand the mechanism to figure out whether it works in people? No. And if it works, great. That's a win too. I think Rich's point is, we only have so much money. Let's spend it on figuring out the mechanism. But that's a fundraising issue.
It's a scientific question. If you have a choice, the ITP loves to test individual chemical compounds, even sometimes ones where the mechanism of action is not known. And that's very sensible. We are very dubious about, let's take a little of this and a little of that and a little of that. And we're really dubious about let's grind up the asparagus. Who knows what's in it? Let's see if it works.
And yet you guys have tested natural products where we have no clue what the mechanism is, or even metformin. You pointed to complex 1 inhibition. Yeah, that's one thing metformin does, and it might activate AMP kinase, that mechanism. I'm not saying
we have
no
to know
clue.
the mechanism exactly of each drug. What I'm saying is that if you have a very complex mixture of hundreds of molecules and something happens, you don't know what to do next, because it could be any 1 or 2 or 8 or 10 of those, and you haven't really decided. You have troubles then with standardization, with mechanistic tests, and with transferring to a key species like humans.
My thought is we still wouldn't be using anesthesia if we had to wait until we figured out how it worked.
Yeah. I mean, I think, and it doesn't have to be parabiosis. It doesn't have to be, taking blood from young people and putting it into old people, right? There are other variants of this that can be done clinically. And there's some evidence to support things like therapeutic plasma exchange or things like that. So should we test it? I think so. And my gut feeling is, yeah, it probably will have some benefits.
So if you could only do one experiment, would you do a plasmapheresis experiment? And if so, what would you would you test? I mean, the simplest one is you literally just exchange old plasma for albumin, right? That's what they're typically doing in these studies.
Yeah. I mean, first of all, I don't know enough about this area to be confident in my answer, but yeah, that's probably where I would look to start, simply because it's going to be logistically easier to do from a clinical trial perspective.
So scientifically then, the hypothesis is it's the presence of something bad.
Well, it's both.
That is worse than the absence of something good.
I don't know,
because the albumin's not going to give you the young person's
That's the
whatever,
problem
right?
with that experiment to me. We don't know now.
Yeah, we don't.
If it's young blood is good, old blood is bad, or some combination. We would automatically, if we only did the plasmapheresis, we would only be testing part of that.
I'd push back on that. I think we do have reason to believe it's a combination of both. There's data in both directions. So,
right.
So
right. That's why I proposed starting with the
I think that's, again, as much as anything's sure in this field, it's not as sure as rapamycin increases lifespan in mice, but there's at least evidence to support that idea.
Right.
And the last thing I'll say is you asked why might it fail in humans. I think Steve's answer is valid. It's also worth mentioning, at least with the parabiosis experiments, the parabiosis experiment itself shortens lifespan in rodents. And so the fact that you're surgically connecting these animals together. So it may be that the benefit from parabiosis, true parabiosis in that context, is somehow related to the shortening of lifespan due to the procedure. I don't think that's the case because there's other lines of evidence that argue against that. But there may be something about the procedure itself that is impacting the outcome.
Increases muscle repair and improves cardiac function. It just seems to me that's,
I agree. I'm just saying that may be an alternative explanation for something that's limiting in those mouse experiments.
Just seems like there's not enough time and not enough money to do the work. Hopefully some of that's changing. If we were to do another longevity roundtable next year, which is problematic because this table, I mean, you guys are going to have to get awfully cozy. Any nominations for folks you'd want to invite to a longevity roundtable next time? There's so many people we could do this with, right? And I'm guessing nobody wants to give their seat up next year or to make this table bigger.
I think it would be good to invite Vadim Gladyshev, because I think even though I disagree with some of what he says, I think he always has something interesting to say.
Who's your nominee?
I'd need some more time to think about it.
Matt, anybody jump in?
I think we would all agree there are tons of great people in the field. I mean, I think Brian Kennedy, and I think Brian's going to be on your podcast in an upcoming date, is somebody who also thinks broadly and deeply about the science and is fantastic. So he would be great to have. It would be great to have some differing, I mean, we differ sometimes on opinions, but I think more or less are aligned. Be interesting to have some differing voices as well.
All right. So we think we'll do another longevity roundtable around the oval table?
Sure.
Let's do it. Let's see where we are
I think in a year from now, I think there's going to be a lot of new stuff. That's what's new in aging research. The rate of progress.
The derivative is very much positive.
You know who else I want to throw out there is Morgan Levine. I think she'd be really interesting to have because while she is an expert in epigenetics and biomarkers, I think takes a pretty clear-eyed view of that space.
Now, is Morgan at Yale still?
She's at Altos.
She's at Altos. Yeah, okay. I wasn't sure if she was there full-time. Got it. Okay.
Yeah, I would second that. That's an excellent idea.
All right. Well, Rich, you can get back to me on your nominees as well.
I will definitely do that.
All right. Gentlemen, thank you for
nominee
making
committee onto this, and I'll get back to you.
Thank you. It was fun. A lot of fun.
All right, guys. Thank you.